Small lights have a way of being seen in a dark world. Now let us light the lamp, formally inaugurate the today's workshop. So we are going to light the lamp digitally.
Can we see?
Just
We
a
can't
minute,
see, no?
we are trying. Here the screen where to all participants. Share the screen. Can you see my screen?
Yes.
Yes.
No, we can't see.
Right.
Is it
Yeah.
okay now?
Yes.
Yeah.
Yes.
Yeah, now.
2 minutes.
Voice aikata.
Yes.
Very nice.
You're muted. You're muted.
Yeah. And thank you, one and all. We have already inaugurated with lighting the principal to welcome and introduce our guests. Sir, principal, sir.
Okay. Dear teaching fraternity, research scholars, and students who are participants of this National E-Workshop on Lasers and Optics, a very warm welcome to you all. And we are all honored to have outstanding scientists, eminent academicians, and research scholars who are with us as resource persons, chief guests, and guests of honor. Certainly, Indian Academic Degree College Autonomous Bangalore is privileged and honored to have such an outstanding scientist and research scholars amidst us. I am glad to welcome each one of them, to begin with Dr. Lalitha, the chief guest of this national workshop. We understand sometimes few of us will be wondering, why do we require a formal inauguration? Being a national e-workshop for a full day program, it is very important that we honor and acknowledge the presence of distinguished personalities, particularly Indian Women's Scientists Association of Bangalore chapter, with whom we are collaborating from the Department of Physics of Indian Academic Degree College. And I'm glad we have two presidents with us, the former and the present. Dr. Lalitha, who is the chief guest for this inaugural session, is the present president of Indian Women Scientists Association. Briefly, I will introduce a little later about Dr. Lalitha. Hearty welcome to you, ma'am.
Thank you. Thank you very much, sir. Thank you.
I'm delighted to welcome Dr. Devaki Ramanathan, the guest of honor, as I said, who was the former president of Indian Women Scientists Association. She too is a senior scientist, former technical physicist and prototype engineering division of BARC. She is a member of Board of Trustees of Indian Women Scientists Association.
Thank you.
We are honored to have you with us this morning. A hearty welcome to you, ma'am. We also have with us the CEO of Indian Academy Group of Institutions, Dr. Srinidhi Parthasarathi, in his capacity as the Chief Operating Officer. He has joined us to preside over this inaugural session. He is a research scholar, an academician, an orator. Above all, he is a very good human being who understands people from his heart. We are delighted to have you with us, sir, this morning. I'm happy that you have accepted to preside over this function. Hearty welcome to you, sir.
Thank you, Dr. Siram. Thank you.
In addition to these three eminent personalities, we have two fantastic research scholars, scientists from, again, BARC, Dr. Padma Nilaya, head infrared laser section, who will be introduced to the audience during the latter part of the day. Very warm welcome to you, ma'am.
Thank you very much.
We are happy that you have accepted to be the resource person for today's e-workshop. Thank you so much.
My pleasure.
We are also delighted to have Sri Asim Singh, a scientific officer in the Department of Laser and Plasma Technology Division, Baba Atomic Research Center. Sir, it is an honor to have you with us this morning, as you too will be one of the resource persons for the day.
Thank you.
While welcoming these eminent personalities, I would like to also welcome the chairperson or chairman of Indian Academy Education Trust, Dr. Somshekhar, who himself is a scientist in biological sciences. We are happy to have our chairman, the secretary, who are members of the Indian Academy Education Trust and who have given us the opportunity to have this program. Let me briefly introduce the chief guest. Dr. Lalitha the Rashford is a retired head of Laser and Neutron Physics Division of BARC till 2010. It is an honor to have not only an outstanding scientist, but she seems to be an all-rounder. She has involved herself into the spiritual development and value-based education of young generations of India, and she has contributed to the development of communities around her. To share some of the salient features of her profile, she was Raja Ramanna Fellow, Department of Atomic Energy, BARC, for 5 years. Having completed her PhD in physics from the University of Mumbai, she joined BARC after completing BSc from the University of Bangalore in 1969. Dr. Lalitha worked for 45 years at BARC in the field of high-power laser plasmas and applications, and was instrumental in carrying out several prestigious projects. As a PhD guide for University of Mumbai, she has guided several students to obtain their PhD. She has over 75 publications in the reputed international journals. She had been invited by international laboratories and universities in USA, Japan, Germany, France, Russia, Spain, Italy, Poland, and so on. The list goes on and on. Dr. Lalitha is the current president of Indian Women Scientists Association an NGO which has the main mandate of taking science to society, empowering very specially women, and nurturing talent among school and college students. Dr. Lalitha is a member of Heartfulness Institute, a spiritual organization for the last 29 years. As a preceptor and certified spiritual trainer and self-development facilitator and mentor, she imparts spiritual training through heartfulness meditation. She has conducted numerous heartfulness and self-development training programs all over India. For her contribution to community service, she was honored by Rotary Club, Lions Club, Canada Saraswat Association, Amity University, Modern College, Pillai Group of Institutions, MGM Group of Institutions, Anjuman Islam College, and by various other associations, universities, and institutions. Dr. Lalitha, it is certainly not only an honor and privilege, but we are truly delighted to have such an outstanding all-round personality in the form of you, who holds the position of chairman for this association. It's good that we are honored to associate ourselves with you and able to conduct this e-workshop for the teaching fraternity, students and research scholars. The guest of honor is Dr. Devaki Ramanathan, is yet another physicist. She retired as a senior scientist from Bohr. Her specialization was in ultra vacuum technology, surface science instrumentation like field emission and field ion microscopy, and PBB level mass spectroscopy like ICP-MS and GDMS. Besides a huge number of publications in the international reputed journals which are to her credit, it is noteworthy that she has published on FIM, the prestigious Nature journal, way back in 1977. Certainly, you are an outstanding scientist, ma'am, and we are honored to have your presence with us this morning. We understand that you have co-authored books, and even after retirement, you continue to lend your service to the student fraternity as well as teaching fraternity, very specially to the women and the girls through IWSA. You were the former president for 2015 and 17, and you continue to be the board member, and we are happy to have you this morning with us. And we hope to listen to both of you, the wise women from the West. Have a beautiful day, madam. And as I said,
Thank you.
we also have with us Dr. Sriniti Parthasarathi. I have already introduced him briefly during his presidential address. He will share his wisdom and knowledge with the participants as well as with us all. Thank you. Have a wonderful, resourceful, and meaningful e-workshop. I hope all the participants will learn much through the rich experience of these two resource persons who are there with us this morning. Thank you very much, and God bless you all. Over to Dr. Banita.
Thank you, Shar, for giving such a wonderful introduction and welcoming our guests. So now I request Dr. Lalitha the Rashford to give the chief guest address.
Yes, thank you very much. Dr. Jerome Xavier, Principal of the Degree College, Dr. Parthasarathi, and of course, Dr. Banita. And I'm very happy to be here with my ex-colleagues, Dr. Padma and Shri Rawat ji, who readily agreed for, this taking part in this program. And I'm very thankful to the college, Indian Degree College, Indian Academy Degree College, And I would like to share a few experiences and what I think about, lasers in general before the experts give their contribution and talk about the lasers. To tell you, the invention of laser has provided us with a very powerful and new tool for research in so many fields. When the laser came into existence, took its birth, it was called a solution in search of a problem. That means it could address any problem and it could contribute to any problem. So the research in the areas of physics, especially in the laser Raman spectroscopy, photochemistry, biological science, in the medical field, and the atomic physics field, where there are hardly any experiments where laser is not involved. Almost in every modern experiment in research involves the laser system. So over number of decades, it has, evolved to such an extent that hundreds of lasers have been invented and they are being used in thousands of applications. For example, in medical applications, all of you are very familiar that surgery with retinopathy for detached retina, fixing it back, is very well known. Refractive surgery, where just a small nick with the laser beam can cure the astigmatism and the problems with the lens, eye lens. All these have come up after the laser has come in the picture. It is called the laser scalpel, for the surgeons. And in dentistry, for doing minor operations on caries, tooth whitening, cancer treatment, photodynamic therapy, laser angioplasty for the heart surgeons. It is very common nowadays. Laser tweezers, for which the Nobel Prize in 2018 was given to Arthur Ashkin, where he could hold a small molecule with the help of a laser beam by the light pressure created by the laser beam and do whatever you want, under the microscope. And you can actually manipulate these small molecules. To that extent, lasers have been used. And in engineering, it is now very widely known that almost every industry now uses laser for cutting, welding, drilling, surface modification, 3D printing, and civil engineering also. And in military also, we have, laser range finders and ranging, which are mounted on top of these tanks to range the distance between the enemy, tanks and then fire the weapons. And we have laser guided missiles also from aircrafts. And we have directed energy weapons, which are used directly to attack the enemy. Those are also very well known in the modern day. And in the energy sector, in especially nuclear energy program, laser-based new fusion has taken a big, it's become very important. And several laboratories in the world, the top laboratories, are focusing their attention on this. In the communication field, everybody knows now, you have your optical fibers coming right up to your homes via, Geo is providing and many others are providing to have a very large bandwidth laser optical communication systems. And satellite communication, of course, is in place, very much placed because of the lasers. And in the environment side, geo mapping, the LIDARs, the laser terrain mapping, pollution of air and water, determination of that, and mapping of that, that also has been done by lasers. And space technology is full of lasers, you just, when in 1969, when Apollo 14 landed on the moon, a retroreflector was placed on the surface of the moon, and the exact precise measurement of the distance of the moon from the earth was done using the laser, a ruby laser. Three-dimensional photography or holography is also very well known. Everyone knows about this. And in general, everyday life, we have lasers almost everywhere. The laser printers, the laser pointers, the entertainment sector is using lasers. The traffic policing, speed of vehicles are measured by the laser radars, barcode scanners in the supermarkets, the compact disc CDs, the security alarms which are being used, all of them, they are using lasers, and the list goes endless. It's almost endless. Now, what has laser done actually? It has actually revolutionized optics and revolutionized many of the fields in which modern research. And some of the most important contributions of lasers is in higher harmonic generations and communications using fiber optics. Because of fiber optics, now you can have transatlantic ocean fiber communication systems, and communication system between two continents has become so much easier. And also, there is a new field which is called the intense lasers to generate extreme states of matter, where nuclear fusion is concerned, where you can fuse the two nuclei, deuterium tritium nuclei, in the laboratory and create conditions similar to the sun in your laboratory. Here, intense lasers are being used, where they generate extreme states of matter and they become study. You can study matter at such intense, state of pressure and temperatures. You can actually see how they behave and you can study them, and you gather a lot of information through that. And it's not just lasers in the visible, but X-ray lasers are also been made possible after the laser came into the picture. And the shortest wavelengths they have gone up to is 0.15 nanometers. That is almost 1.5 angstroms. And that is the kind of, so you can imagine what kind of systems you can study using these lasers, X-ray lasers. You can study atomic structure of materials. You can study defects and so many things. And free electron lasers have also come, where a lot of exciting research is taking place. And this free electron laser, or it is called FEL, is called the 4th generation synchrotron light source. You have heard of synchrotrons, which give rise to X-rays. And in India, we have 2 synchrotron sources, Indus 1 and Indus 2 at Raja Ramanna Center for Advanced Technology at Indore. It is called RRCAT, where the X-rays generated from the synchrotron light source is being used for various applications. Medical imaging is one of them. Industrial imaging is one of them. And it is kind of very high speed X-ray photography, or for X-ray tomography. This kind of experiments are possible using the synchrotron lights facilities. And the size of the synchrotron is really very huge. It is maybe huge building in which the synchrotron facility is housed. But a free electron laser facility is perhaps maybe 1/4 or 1/10 of that size. And you can produce brilliant and short pulses of laser using such free electron laser facilities. It behaves in many ways like a laser, this free electron laser, but instead of using stimulated emission from atomic or molecular excitations, it employs relativistic electrons as the gain medium. It's something which is wonderful, if one wants to study this, one can easily get several review articles in this. And I feel X-ray lasers and free electron lasers are the future of, in the laser fields. So on the whole, these are called super fast, super powerful lasers, and they are revolutionizing physics. And it is said that they will serve as the hearts of discovery factories. So this was told in one of the Scientific American issues dated March 19 to 2020, very recent Scientific American issue, where they call the lasers as the discovery factories for the planetary science, for astrophysics and material physics, fusion, and much more. So it is, you cannot think of what the lasers can do in the future. You can maybe think of, the Star Trek, many of these, you must have, as students, I'm addressing the students, you must have watched many of the Star Trek episodes where the lasers are being used very frequently for various things, maybe for beaming the people up and down from the satellite, from the spaceship to the planetary system or whatever it is. Anything is possible. But science is on one side. Now, I would like to bring to notice to you something a little away from this. Science, you will be able to get it from every book. You can read the articles. But what is the contribution of the scientists to the world? Who are these scientists? What is the special ingredient which is there in there and characterizing, which is part of their character, which makes them what they are, and they contribute to this extent to the world? Because if you see, this is the case with almost every scientist. If you see the life story of these scientists, it is so full of wonder and so full of, things which are really inspiring to us. For example, if you take laser, now that we are talking about laser, where did the laser history begin? It started way back in the last century, 1917, more than 100 years ago, when the key to the invention was the concept of stimulated emission, which was given or introduced by Einstein. And Einstein's insights into the interaction between light and matter, which was discovered more than a century ago, led to invention of the wonder ray of the century, the laser. By theoretical analysis, he found that, you have absorption processes, that is interaction of light and matter. Absorption is going to take place when you shine any medium with light. And he suggested, or he proved, or he theoretically brought about the concept that a complementary process can also take place along with the absorption, implying that the received radiation can stimulate the atoms to emit the same kind of radiation, which is a possibility. In this process lies the potential means for amplification. However, the stimulated emission was long regarded as purely theoretical concept, and people completely ignored it for a long time, saying that this is impossible. And because absorption is going to be dominating process, how can it, it's a normal condition. If you have to have an amplification, then the stimulated emission has to be larger than absorption, which in turn requires that there should be more atoms in higher energy state than in lower one. How is it possible? It flouts the Boltzmann distribution. It cannot happen. It talks about a negative temperature. How can it be? So the scientists did not look into this for a long time. And they said that such an unstable energy condition, it is called inverted population. How can it happen? Till a scientist called Charles Townes in 1953 studied this, and he made an ammonia maser. That means the principle was the same, stimulated emission, but in the microwave region. That is why it is called microwave amplification of stimulated emission of radiation. And he made it operational in microwave region at a wavelength of 23.786 gigahertz. This was actually made operational by one Professor Ziegler, Charles Townes, and James Gordon. They were all together in this particular. And it is the Nobel Prize was given to Charles Townes. And at the same time, Professor Basov and Prokhorov from Russia, from Lebedev Institute, were also working in parallel to bring about this laser. And they also equally contributed. And all these three of them, they were awarded the Nobel Prize in 1964. That was the first Nobel Prize given for three scientists working on lasers. Though Theodore Maiman, who was, working at the time, around that time in Hughes' lab, he invented the first laser, that is in light amplification by stimulated emission of radiation in the visible region using a ruby crystal. So it was called a ruby laser. He did not get the he did not get the Nobel Prize, unfortunately, but he got several other awards, because that became the stepping stone for actually operating lasers in the laboratory in a very, very small scale, very compact lasers. He was responsible to actually bring lasers to the commercial arena also and manufacturing sector. And he built the laser industry in America, to say he was the first person who joined the Corad Corporation at that time, which built these high power ruby lasers from every component. They grew the ruby crystals. They made those flash lamps, helical flash lamps, which were needed for these making the ruby lasers. And in the electronics, the electrical power supply, everything was made by Corad Corporation. And this man, Theodore Maiman, was in charge of this entire program. In 2007, actually, Theodore Maiman, he passed away in 2007 at the age of 80. And in 2007, in an obituary testimonial, the major co-inventor, that is Charles Townes, described Maiman's 1960 Nature article, which he had published on laser, probably more important per word than any of the papers published by Nature over the past century. I think this was the greatest compliment that a scientist can get for his work. So whether he gets a Nobel Prize or not, it does not matter. But you see the amount of praise and the amount of laurels that he got from his co-workers. In 2011, he was recognized by the Stanford University. He was the alumni from the Stanford University as a Stanford engineering hero. And in 2017, UNESCO declared May 16th the International Day of Light, which is celebrated every year by numerous laser and light related events around the world. So maybe next year you can also celebrate, your college can also celebrate the International Day of Light on 16th of May. And very interesting, now coming back to Charles Townes, who was the Nobel Prize awardee, who actually, he passed away. He lived almost 200 years. He was born on July 28, 1915, passed away on January 26, 2015. And just before the laser came in the scene, when he actually made it operational, I believe he stayed in his laboratory for 3 months. He did not go home. He was actually in his life story, his wife has said that she used to bring everyday food for him, and he slept in his lab, he lived in his lab for 3 months and did not go out of his laboratory for 3 months. And it's very interesting, if you look at the life of Charles Townes, he said his opinions concerning science and religion. He was a person who kind of science and spirituality he brought together. And he expounded in many of his essays the convergence of science and religion. Why I'm telling you all this is, scientists are believed to be atheists and non-believers, but many of them have been great philosophers, including Einstein himself. They believed in nature's greatness and the work that nature does, which is impossible for a human being to understand at all levels. So what did Townes say? He said logic and uncertainties in science and religion. He brought it out, this particular essay, in Making Waves. If you get a chance, please download this book, Making Waves by Charles Townes, and read this. Because when we read the life stories of these great people, we get a lot of inputs and lot of great inspiration. I can remember from my own life, in 1968, when I was in the second year of BSc in the Central College of Bangalore. I was your age, you students, and Professor C.V. Raman, the Nobel laureate, he gave a lecture on lasers to us, and it was a spellbinding lecture. Then and there, I made up my mind that I will spend the rest of my life studying lasers. And it became true. See, you never know when the aha moment can come in your life and when the whole life can be changed. And what Townes says is, first of all, he argues that faith is a very important thing. And he says the scientist has a faith, much like a religious person, allowing him to work for years for an uncertain result. Imagine a person, a scientist, works for 15 years, 20 years without knowing whether he will be really successful or not. Even Madame Curie, I mean, the amount of work they did, even without knowing whether they will be successful or not, it is stupendous and a revelation. And he claims, Towns claims that many important scientific discoveries, like his own invention of maser, occurred as a flash to him, much more akin to the religious revelations that happen to many of the people, saints, and many of the people who have always claimed about this. And perhaps it is possible. It is in most of the discoveries, has happened, like Archimedes. He also, when he was relaxing in the bathtub, he came across this idea of buoyancy. And so similarly, for so many scientists, this can happen. And over 6 decades, Dr. Towns, worked for on various aspects of radar, bombing systems, navigation devices during the World War II, and advised the presidents of the country and government commissions on lunar landings and missile systems. And he verified Einstein's even cosmological theories, discovered ammonia molecules, and so many. I mean, if you see his research, it is spanning over so many areas. And in New York Times on 28th of January, the next day after his death in 2015, it was said that he had an aha moment, that moment where sitting on a park bench in Washington, one April morning in 1951, pondering how to stimulate molecular energy to create shorter wavelengths. He conceived the idea of a device called maser for microwave amplification by stimulated emission of radiation. It could use molecules to nudge other molecules and amplify their thrust by getting them to resonate like the tuning forks and line up in powerful beams. He and his 2 graduate students, James Gordon and Ziegler, actually they built this maser in 1953 and patented their creation. It was the first device operating on principles of laser, although it amplified microwave amplification. So in his own words, Charles Towns says, I woke up early in the morning and sat on the park bench. It was a beautiful day and the flowers were blooming. And in 1951, Charles Towns, he sat and then on that bench, and that was the time when this occurred to him. This is something really great, moment. I think that was the moment which has given us lasers. So in 5 years later, Dr. Townsend Shallow was his brother-in-law in his real life. They would win in 1964. He won, Shallow won the Nobel Prize in 1981 for the work on laser spectroscopy. They drew a blueprint for laser. They called it an optical maser, a term that never caught on and in Bell Laboratories. And he always complained that people, before he made the laser operational, nobody would believe him. He would keep telling, he met so many scientists, so many great people. They would say, how is it possible? So you please, if possible, read How the Laser Happened, Adventures of a Scientist, which was published in 2002 by him. And it will really reveal so many aspects of, how scientists work. The other Nobel Prize in the lasers I would like to bring to you, her name is Donna Strickland, and she got the Nobel Prize in 2018. She's the 3rd woman to get the Nobel Prize in 150 years. Marie Curie was the first one. Then Maria Goeppert Mayer in 1963 was the second, and she was, that is Donna Strickland, was the 3rd one who shared the Nobel Prize with her colleague and her mentor, Gerard Moreau, for bringing in the era of intense lasers. They brought about a particular mechanism by which it is called the chirped pulse amplification, by which you can produce lasers which are of peak powers of petawatts, that is 10 raised to 15 watts, and durations of few hundreds or maybe even few tens of femtoseconds duration. You can imagine what such kind of intensities if it is focused to extremely small spots, what it can do to that material within a fraction of within a nanosecond or maybe picosecond, it goes into the fourth state of matter called the plasma state, and you can study so many processes. And we do have at BARC such a laser system which is working, and and in TIFR also. So whenever possible, if at all, and I think in some of the maybe laboratories in Bangalore also, maybe Indian Institute of Science, you can try out, and you must go and have a visit to these laboratories. And what I want to say is Donna Strickland's first PhD, the first paper she published was in 1985. I have it still with me, filed in my office and lying at BRC. I never knew that she was a woman. That is very strange because she never said she was Donna Strickland. It was always coming as D. Strickland till much, much later when I saw her complete name in one of the programs of one of the conferences which were held abroad. So seeing the lives of so many scientists, what I would like to conclude now is, you have to see some common characteristics which are there, common to all of them. These include first of all, a sense of wonder. And how does one get a sense of wonder? We should be having the time to pause in life. If we are continuously running about doing this and that and this and that, you will never have time to pause and wonder. Maybe sometimes just lie down and then just go into a dreamlike state and think. It is very necessary because even Abdul Kalam said that you must dream big. Only when you dream, you can achieve. Otherwise, you can never achieve what you want to, what you can do, you may not, because dreaming is a very important part of the scientist's life. So a sense of wonder, a strong observation skills, which is very important. Observation, we have to teach our students right from the beginning, that every step they have to have very keen observation. And now under the NEP, the National Education Policy, this has been included as a very important component because they have brought the ECC, the Early Childhood Care Education, as a part of the formal education system in India, where the age group of 3 to 8 children are going to have a formal education, and this will be their anchor. That is a sense of strong observation, the sensory perceptions, an inquiring mind, curiosity. All this has to be, these kind of skills which are there in every human being, they have to be brought out. Without that, a person cannot pursue a scientific career. Logic is very important. Mathematics, creativity, at the same time, skepticism. You should be very skeptical about your own work also and have objectivity. You should not be, because you are thinking, you should not think that, okay, this has to be right. Until somebody proves you wrong. No, you can always have an open mind to accept criticisms from all people around you. These are the qualities which are common to most of and I would say all the scientists. And if you want to make a career in science, this is absolutely essential. So my dear students, I would like to now end here and tell you that this is a short introduction to entirely two wonderful talks that we are going to have today, and the demonstrations. I think the demonstrations are for the first time being carried out on an e-webinar. Otherwise the webinars are always full of talks, and demonstrations and practical, showing practically the experiments is going to be really very interesting to you, especially the students are not able to go in the laboratory and work, but you can at least see on your screen what's happening, and wish you all the best and all have a nice time, have a nice day with the scientific, the resource person telling you so many interesting things, and we have Devaki to tell you about many other things. So with this, I'll end my address here. Thank you very much.
Thank you, ma'am. It was certainly a broad outlook with in-depth knowledge. It was almost like opening a dam filled with water. Your wisdom, knowledge, and experience in the field of laser was keenly observed, and I hope the participants enjoyed as much as I did. It was a great information and knowledge for us, especially who have less knowledge in the field of laser. And on behalf of Indian Academic Degree College, I extend my gratitude and warm wishes to you, ma'am. May you continue to serve the young minds through your community service, which is very important in today's world. A spiritual outlook which will develop overall personality of students. So I'm glad to have seen you at least through this e-workshop. Thank you very much, ma'am.
Thank you. Thank you.
We have our guest of honor, Dr. Devaki Ramanathan, who was the former president of Indian Women Scientists Association. I'm sure she would like to share with us some of her inspirations, thoughts, and wisdom. Let us listen to Dr. Devaki Ramanathan. I think that Dr. Devaki has left us, or?
Dr. Devaki is here. She has a small presentation to make. I think.
Ma'am, I'm doing, ma'am.
Yeah.
Just. Sir, I'm doing that sharing screen. Hello, Devaki ma'am, can you see my screen? It's not happening. 2 minutes, ma'am. I'm trying. What is happening? Share screen. Share screen. Yes, it is coming. Ma'am, Devaki ma'am. Yeah, now. Ma'am, can you see the screen?
Devaki, can you unmute yourself? Unmute yourself. Dr. Devaki, can you unmute yourself?
Okay,
Yes.
I think I was muted all the while. Dr. Bamita, Principal, Professor Dr. Lalitha the Rashford, resource persons from BRC, all students, participants and guests, good morning to all of you. It gives me a great pleasure to present to you our NGO, which is Indian Women Scientists Association, which is acronymed as Imsa, and which is collaborating through its Bengaluru branch for today's e-workshop. Now you can have a glimpse of the IMSA headquarters campus. It's about 6,000 square feet area, a sprawling 4-storied building, our working women's hostel, with an extended activity section. Okay, she has gone to the second slide. But yeah, you can see the activity section, which includes a conference hall, a library, a science lab, a computer facility, health room, committee meeting room, a daycare center, and a nursery classroom. The second slide, please. This is our NGO. Uh, Can I have the second? Yeah. A non-political, a non-profit organization. It was established in 1973 by 12 eminent women scientists who were very senior and who decided to give their knowledge and services to the society through community welfare schemes and a clear mandate, taking science to the masses and working for the empowerment of women. Our NGO is therefore now 47 years old with 11 branches and a total of about 2,500 Imsa members, life members. The Bengaluru branch, there's a Bengaluru branch also, which is relatively young, and the capable Professor Savitri Bhatt, who is the HOD Biotechnology from BMS College of Engineering, is the convener, and it has 37 life members already and is growing. I hope Dr. Savitri Bhatt is present today. I'm not sure. Today's webinar is our Bengaluru branches collaborative webinar conducted for the benefit of your college students. Our campus at headquarters normally can be seen bubbling with students participating. Now, the next slide shows the different community services rendered from IVSA. Can I have the next slide, please? I'm giving only a bird's eye view of our NGO. So this is the community welfare activities. More details, if you want, you can go to our website, www.ibsa.net. And special mention I would like to make of the Early Childhood and Care Education's one-year diploma course, which was mentioned by Dr. Lalitha the Rashford also, which has been run successfully for the last 25 years from our campus. This course is affiliated to the SNDT Women's University of Mumbai, and recently short-term courses also for handling special children, ADHD children and LD students, that is learning disability students. This has also been initiated. Next slide, please. Our science education, next slide, shows our science education initiatives, which are quite varied, starting from school children to college students. Yeah, right, thank you. Encouraging students to imbibe a scientific culture. All programs are aimed to advance scientific knowledge and motivation through different programs which are conducted. Most of our branches also are equally active, conducting programs with enthusiasm and energy. I would like to mention that all activities and programs are carried out by our members as voluntary services. And today's webinar is also the Bangalore branch's collaborative workshop. Our campus at the headquarters normally can be seen bubbling with students participating in different programs. Since last 2 years, a learning garden, I made a mention of that in the slide, a learning garden initiative has been started, which is an open air laboratory, and we plan to provide an environmental and all-inclusive education to school children, college students, and also to the general public, including senior citizens, through direct observation and study of nature and its biodiversity. Now, during the pandemic and lockdown period, we have kept ourselves busy through Wi-Fi, thanks to Wi-Fi, not only to have our regular meetings, but also to have a number of webinars. Can I have the next slide, please? The next slide shows our LG project, that is the Learning Garden project. Next slide, please. Yeah, these are Learning Garden projects which has a Wednesday webinar, which is called MEP, that is Member Enrichment Project. These talks are open to all members and our own school students to mutually exchange knowledge on plants, their growth environment, biodiversity, etc. We have had almost 30 webinars, and these have been really very educative, enhancing our knowledge and expertise. Bangalore branch also has participated in 2 of these sessions. Next slide, please. Next slide. The popular science lectures in different colleges have been sponsored. No, please, the previous one. Previous slide, please. Yeah. Popular science lectures. These are for college students and faculty, and they have been sponsored and encouraged by the BRNS of Department of Atomic Energy, which have been conducted very regularly since so many years at headquarters and also in the branches. Now, of course, in the pandemic times, they have been conducted as webinars, and but their attendance has been very encouraging and gratifying. So we encourage and we motivate the children, the college students, to take up science careers through showing them the latest that is happening in science and technology. Next slide, please. Next slide shows recently we have initiated another series of webinars, which is called Science and Our Life Talks. This is once a month, open to all and even to the general public besides all our members. It is aimed to bring out the science behind all our activities and our life. We had one webinar on the science of creation of wealth. So all these are popular science-based talks, and these webinars are uploaded on the YouTube as Imsa lectures. Next slide, please. I'm really being very brief. You can see the rest of the things on the slides. We bring out a quarterly newsletter. It's a newsletter. It summarizes all our activities, but also includes interesting news-breaking topical articles on science and technology. Our website, again, I'm repeating, is www.ivsa.net. Please become members, open the website to see our current and upcoming events and participate. I'm sure you will find them educational, useful, and fulfilling. Thank you very much. I hope I've been brief enough. Only 5 minutes were allotted earlier, so I have kept my description very short. Thank you.
Thank you, ma'am. Thank you, ma'am, for enlightening us about activities, goals, and achievements of IFSA and IFSA branches all over the India. Thank you, ma'am. So now I request Chief Operating Officer of Indian Academic Group of Institution, Dr. S.K. Parthasarathi, to give the presidential remarks.
Good morning to all of you. Most respected Dr. Lalitha the Rashford, President of Indian Women's Scientists Association. The past President, Dr. Devaki Ramanathan. The resource persons of the day, Dr. Padma Nilaya and Shri Asim Singh Rawat. Dr. Jerome Xavier, Dr. Banita. It is extremely marvelous to be with all of you this morning. In terms of listening to this wisdom quotient from BARC. The entire wisdom quotient is here to bless Indian Academy. Thank you so much for the same. Like how the creator is omnipresent, we heard from Dr. Lalitha the Rashford that laser is also omnipresent. From engineering, medical, communication technology, and one forum which he very passionately belongs to, even in spirituality, laser and its relevance finds a place. Not being a scientist, being from the management field, definitely both the talks which happened now were extremely insightful. I've also come across, glanced through the reference of laser in the Rig Veda and in the Vedic times. When we talk of Tripura Samhara, when we talk of the Indragni missile, references to modern day laser has been given in those. So such workshops have been extremely imperative for the students of today. Indian Academy is a research-oriented organization or institution. Faculty members here are first researchers and then they go to the class. Three important things which Indian Academy focuses on is to generate curiosity in the learners. It's a learner-centric institution. Curiosity in the learner, absorptive capacity is built in the learner, and the learners nurture. Only then they can do something. C stands for curiosity, A stands for absorptive capacity, and N stands for nurturing. The will in the student is built through these three important parameters in the learning space in Indian Academy. I'm extremely happy that the Department of Physics has collaborated with the Indian Women Scientist Forum Association in bringing up this one-day workshop, national workshop. I'm very sure that this is going to be extremely, extremely insightful. Kindly lend thy ears. All the 115 participants whom I'm seeing on this screen now, kindly lend thy ears throughout the day, because what we saw only in the introductory remarks, which is the tip of the iceberg, if that is so insightful, then during the day what is going to come is going to be really revealing and revealing. So thank you so very much for all of you to be with us, and we will have a great day ahead. Thank you so much.
Thank you, sir, for presidential remark. We also thank you for being with us in various activities and inspiring the younger generations to achieve new horizons. Thank you once again.
Thank you so much. Thank you.
Thanks. So now we have come to the end of the inaugural session, and now I take this opportunity to propose the vote of thanks on behalf of Indian Academy Degree College Autonomous. First of all, my heartfelt thanks to Dr. Lalitha the Rashford, my special thanks to Dr. Devaki Ramanathan, the guest of honor of the workshop. Thank you, ma'am. I thank the management of Indian Academy Group of Institutions for the support rendered to us in organizing this e-workshop. Now I thank Dr. Srinidhi K. Parthasarathi, Chief Operating Officer, Group of Institution, for his moral support. I thank our beloved principal, Dr. E. Saram Xavier for his valuable and support. I thank all the members of IFSA for their help and support. Finally, I thank all the faculty members of Department of Physics support. I thank all the participants and for providing technical support. Thank you, one and all. So all the participants will be joining shortly for the first session. After this inaugural session, the first session will be by the resource person, Dr. Padma Nilaya from BARC.
A very good morning to all the participants of the National E-Workshop on Lasers and Optics. I, Mrs. Rama Bharati, Assistant Professor, Department of Physics, Indian Academy Degree College, welcome you all to the first session in which our distinguished speaker, Dr. Padma Nilaya, will give us more insights into laser fundamentals and applications. I now request our HOD, Dr. Banita Behra, to introduce the resource person to the participants. Over to you, ma'am.
Yeah, thank you, ma'am. Dr. Padma Nilaya, Head Infrared Laser Section, Laser and Plasma Technology Division, BARC. Dr. Padma Nilaya, having postgraduated in physics from Nagpur University with highest honors in 1991. She has joined the laser program of Bhabha Atomic Research Center, BARC, in the year 1992 after successfully completing the one-year multidisciplinary training. Since then, she has been working in the field of physics and technology of MIR gas lasers and their applications. Her work is replete with new results with significant academic value and technological novelties. She now leads a group of engaged in the development of new coherent sources of strategic value, laser isotope separations, and laser surface interactions. Till date, she has co-authored well over 60 peer-reviewed research publications, including review papers and book chapters. We welcome you, ma'am. Now I request ma'am to take over the session.
Thank you, ma'am. Can you hear me?
Yes, ma'am.
So, can I share the screen now?
Yes, ma'am. You can share the screen. You can share the screen, ma'am. Is it audible, ma'am?
Yeah, it is.
Okay.
Can you see my screen?
Yes. Yes, ma'am.
Are you able to see the screen, ma'am?
Yes, ma'am, we can see us.
Okay. Yeah. So, I start now then. Yeah.
Yes, ma'am, you can.
Yeah. Very good morning to you all. I would at the outset like to thank the organizers, IFSA, Dhareshwar madam especially, for inviting me here and allowing me to interact with you young students. It is indeed a great pleasure. So thank you. The topic for today is laser fundamentals and applications. And at the outset, I would like to acknowledge Dr. DJ Biswas, who was my superior here, and he introduced me to laser and laser fundamentals itself. He's also my PhD guide and mentor. I would also like to acknowledge Dr. Pallavi Raute, who was the first Mumbai University PhD student from our laboratory, and with whom I again went through these laser fundamentals. And she also has made 1-2 slides, which I'll be using here, and I gratefully acknowledge. I'm actually thankful to Dhareshwar madam because she has made my job so much easier by actually giving a sort of introduction to my talk itself, in the sense that she told about fundamentals of laser and a lot about laser applications. But then, yes, I'll go through mine. So my talk will also have the first part being an insight into the physics of lasers, which will of course encompass the absorption, emission, amplification processes, the cavity modes, gain, spectral narrowing, which is the signature of amplification by stimulated emission, which will ultimately lead us to the properties of laser. I would also describe very briefly the levels that participate in the lasing process before going on to generation of some new coherent sources by nonlinear processes. Then I would also touch upon laser applications. There are innumerable number of applications, but I would just go through few which are of my interest and probably which will interest you as students as well. Nature, we all know, is one of the most prestigious journals, a weekly which is published from Great Britain. And many of the scientific breakthroughs of the 20th century were first reported in this Nature journal. A Century of Nature is a volume that brings in together the greatest hits of nature in the last century, the reproduction of seminal contributions that have changed science and the world. And laser very rightfully occupies the 8th position in this particular volume, and that speaks immensely about the contribution of laser in not only research, but in bettering the life of mankind. If I have to describe laser in a very brief manner, then I would say this. The laser is an elegant yet awesome tool that has provided seemingly magic solution to numerous problems since its invention in 1960. Powerful lasers destroy airplanes in flight and slice through heavy steel as if it were cheese. More delicate and precise lasers placed in the hands of skilled surgeons can repair detached retinas in the human eye, stop bleeding deep inside a patient's body. Lasers read supermarket barcodes in automatic cash registers, measure the distance to the moon with incredible accuracy. But then, what is this laser? How does it work? And what is so very special about the light it produces? Let us try to understand and answer some of these questions at least in the next half an hour or so. The most appropriate thing to discuss, consider at this point is the operation of a conventional light source. Let us consider a fluorescence light tube. A fluorescence light tube is nothing but a glass tube in which we take a neutral gas species at a low pressure. We say neutral gas, but then one cannot avoid the presence of stray charge carriers inside for obvious reasons. So when an appropriate voltage is applied longitudinally across the discharge tube, then in presence of this electric field, these stray charge carriers get accelerated, and this acceleration is given by the product, the charge into the electric field divided by the mass of the carrier, charged particle. And therefore, the electrons get accelerated, move towards the positive electrode, and in this process, they gain kinetic energy. So when an electron gets sufficiently high kinetic energy, then it can actually collide with the neutral atomic species and then can ionize it. So in this process, it creates an ion and another electron, its own energy having been reduced. So now what you have? You have two electrons, and these electrons can once again get accelerated in the electric field, ionize more, produce more electrons, and in this process, there'll be an avalanche of electrons in this tube, and very soon a current starts flowing between the two electrodes, and we say the discharge is stuck. Now, not all collisions that electron has with neutral species will be ionizing. There will be some which can be inelastic too. That means the electron loses its kinetic energy as internal energy of the atomic species. That is, the atomic species gets excited to the next electronic level. It cannot stay there forever. It is an unstable state, and therefore it makes a downward transition, giving out the difference in between the two energies of the two levels in the form of a photon. This is a random process, and therefore the photons are emitted in all possible directions, 4 pi solid angle around the tube, and that is why we use this fluorescent tube for illuminating purpose. That is, we use it as a viewing source. Now, the obvious question is, can these excited atoms be made to emit in the same direction, all in the same direction? Then it would become a very unique source, because the divergence of such a source is going to be very negligible, and therefore the intensity from that source, that is power per unit area, can be very high, and the brightness, which is power per unit area per unit solid angle, is also going to be immense. So is such a thing possible? The answer is definitely an emphatic yes, because we know that way back in 1917, Sir Albert Einstein, he visualized the possibility of stimulated emission, and probably it took almost 40 years for an American physicist, as Madam was referring to, Theodore Maiman, who was working in the Hughes Research Laboratory, to operate the very first laser, which was a ruby laser, in 1960. And the first laser flashing its light fired the imagination of scientists, and the laser aptly was nicknamed solution which is in search of problems. Now, I was saying that an electron which is sufficiently energized can excite an atom. The same can also be done by making use of a photon of the right frequency, such that the energy of the photon is equal to the difference between the energy levels of the excited and the lower state of the atom. So when an atom is impinged, or it interacts with the photon of that particular frequency, then it gets excited. And in the excited level, depending on the properties of the level, the atom, etc., this excited level has a definite finite lifetime called the spontaneous lifetime. So once this spontaneous lifetime is decided, the atom makes a downward transition, and it emits the difference between the two levels in the form of a photon. Now, this is a spontaneous statistical random process, and therefore the emitted photon goes in all possible directions, and this process is called spontaneous emission. Now, the same excited atom, while in the state of excitation, if it interacts with another photon, whose frequency is identical to what its own can emit when it comes back to the lower state, then this second photon can stimulate the emission of a photon by this excited atom in a time which is much, much shorter than its spontaneous lifetime. Okay, so because this atom is being forced to emit, this process is called stimulated emission. And the most important feature of stimulated emission is that the photon which is causing the stimulated emission and the photon which is emitted as a result of stimulated emission, both are identical in all respects. They travel in the same direction, they have the same frequency, they have the same polarization, they are indistinguishable. So this is stimulated emission. But laser is light amplification by stimulated emission. So let us see how this stimulated emission can be used, can be exploited to amplify light. For that, let us consider two situations. In the first situation, we have a medium where the population in the lower level is much, much higher, far exceeds that in the upper level. This is a very natural condition. That is what naturally, normally occurs in nature. And let us shine this medium by a bunch of resonating photons. When I say resonating photons, I mean that the energy of each photon is exactly equal to the difference between the energies of these two levels. So when this group of photons pass through this medium, they can be absorbed by the atoms in the ground state, and which can then go to the upper state. So as this beam passes through the medium, it will be absorbed. Therefore, the transmitted beam will be attenuated, and such a system will act as an absorber. On the other hand, suppose we have the system where we have created more population in the excited state than in the ground state. We have to work to create this situation, and this situation is called, we say that we have created an inversion in the population. And let us have the same beam of photons now incident on this medium. Now, once again, because the frequency is, the energy of the photon is resonating with these energy levels, then this photon can cause stimulated emission of the atoms which are in the excited state, force them to come down, emitting photons of identical frequency traveling in the same direction. So in this process, as this beam passes through it, more photons are added to it traveling in the same direction, and therefore we say that the output gets amplified, and we say that the system is now working in the form of an amplifier. So what we need to amplify by stimulated emission, we need to have an inverted medium where we have created population inversion, more population in the higher state as compared to the lower state, and we need to have a beam of resonating photons, which when passed through this medium will cause stimulated emission and get amplified in the process. Therefore, understandably, higher is the inversion in the medium, higher is the amplification. Every amplifier, we normally associate a gain with it, and therefore this gain of this amplifier will increase with inversion. So if this is light amplification by stimulated emission, then we seem to be requiring an input beam of resonating identical single frequency photons. So what is this then, a laser itself? Do we require a laser to operate a laser? That is ridiculous, because then a laser would never have come into existence. So we know there is a catch here, and for that, to understand what it is, we have to introduce ourselves to a concept which is called the cavity. A cavity is nothing but a pair of resonating parallel highly reflecting mirrors, so separated by a particular distance. So let us consider a typical cavity here. The two mirrors, 95% reflecting, are placed at a certain distance, and we have an input light beam of 1 watt power. So when 1 watt is incident on the front mirror, 95% reflecting, 95% is reflected off, and maybe 50 milliwatt will enter into the cavity. Of this 50 milliwatt, 95% is again reflected, and what you have will be a meager 2 milliwatt. So for all practical purposes, we see that this cavity is not at all transmitting. So what is so special about this cavity? Well, to understand the secret of this cavity, we have to do a small experiment, and that experiment will require a tunable source of light. What is a tunable source of light? A light which is capable of generating output which can be varied in wavelength. So it is tunable in wavelength. So let us assume that 1 watt tunable source of light is incident on the front mirror, and we have a detector which measures the power transmitted by this cavity as a function of wavelength. So the result is summarized here. We see that for most of the wavelengths, this doesn't transmit any output. So this is similar to what we have thought a little while ago. But for certain discrete wavelengths, we see that the transmitted power by this cavity is almost same as what is input to it. That means if it is 1 watt input, you get the entire 1 watt output. So for these particular frequencies, the cavity is said to be in resonance. Okay, and these wavelengths are called resonating wavelengths. Therefore, if we have a resonating cavity, then for that particular wavelength, it acts as a transparent window. Everything is transmitted to the other side, whereas for non-resonating frequencies or wavelengths, everything is reflected off and nothing comes out. Now, if you look at this figure a little carefully, then you will easily understand that those particular discrete wavelengths for which the cavity is resonant, you will see that an integer number of half wavelengths of those will exactly fit into this cavity of length L. That is, for this particular wavelength, the to and fro oscillation between these two mirrors forms a constructive interference. There is a standing wave pattern that is created, and these cavity modes or these particular wavelengths do not decay as they pass to and fro between these particular mirrors. Whereas for any other frequency, there would be a destructive interference due to this round trips between the two mirrors, and they would eventually decay. So this can be mathematically represented in this form: n lambda by 2, where n is an integer, is equal to the length of the cavity. In terms of frequency, it becomes nu n. The nth frequency is nc by 2l. So these frequencies are called the cavity mode frequencies, which are specific to this particular cavity of length L. And each cavity will support infinite such frequencies, nu n plus 1, n plus 2, and similarly this side. And the separation between these two frequencies, which is called the free spectral range of a cavity. It is given by the separation between the two. You can easily deduce it is C by 2L. Therefore, smaller is the length, larger is the separation between the successive modes, and vice versa. At this point, an obvious analogy that strikes us is that of an electron which is orbiting in a Bohr's orbital around the nucleus. You see, any accelerated charge particle should emit radiation, should lose energy, and therefore an electron too should be no exception. It should lose energy as it is going around and eventually fall into the nucleus. But this never happens, and that is because these specific orbits are called the Bohr's orbits, the stationary stable orbits, where the de Broglie wavelength of the electron exactly fits integer number of times onto the circumference of the orbital. Only those orbitals are stationary, and the electron revolves around the nucleus without any dissipation. So you may still feel that fine, we have such a kind of cavity, but yet the front mirror is 95% reflecting. So how is it possible that whatever is incident on the front mirror, all of it comes to the output? Well, you see, initially we have a continuous beam of input. So when you have the initially when you put the beam on the front mirror, the intracavity flux is 0. That means the number of photons per unit area per unit time here is 0. But as the beam is continuous, a small fraction of it, 5%, trickles in. That goes back and forth between the two mirrors, and because it is constructively interfering, the intracavity flux goes on increasing, and it gets added each time with the input in phase until the intracavity flux rises to an equilibrium value. And for 1 watt input that we have considered, the equilibrium value of the intracavity flux is 20 watt for this kind of reflectivities. And therefore, what is 5% of 20 watt? It is 1 watt. So under equilibrium conditions, once the intracavity flux is reached, transients are over, you will see that whatever is input to this particular cavity, if that is a resonant frequency, then the entire thing is transmitted. So from here now, and already you know probably a little of laser, so you probably now can think how a laser can be constructed, right? So a laser is nothing but a cavity where you have two highly reflecting mirrors. In fact, one mirror is 100% reflecting while the other one is partially reflecting, and sandwiched between these two mirrors is the active medium. What is active medium? The medium where we have created population inversion. Okay, so the only difference between this and this is that there is no input now. So without an input, what is this going to amplify, and what are you going to get now as an output? Well, when we have created population inversion, we know that we have created population in the excited state, and the excited state has a definite finite spontaneous lifetime. So the atoms which are in the excited state will spontaneously emit and come to the lower level. These spontaneously emitted photons they can be in all possible directions, but there would definitely be some then along the axis. Now, as the spontaneously emitted photons go along the axis, they encounter more atoms in the excited state. So they stimulate them to emit, creating more photons, which are also traveling in the along the axis. So this continues. There is more stimulated emission, more photons along the axis, more stimulated emission, more photons. And this bunch of photons will also go back and forth between the mirrors, and the intracavity flux reaches an equilibrium value, and we have a steady output, which is called the laser output. So now, you know now what a laser basically constitutes of. You have a medium, the right medium, where you have created population inversion, and you have a cavity where this amplification takes place in a much more efficient manner. Now, let us see how the frequency of this emission it looks like. We have created inversion between two levels, and therefore transition of an atom from this level to this level should give rise to a photon of frequency, which is E0 by the Planck's constant h. So we assume that the emission of the laser should be on a single frequency. Is that true? No. You already know that we already have said that the upper level has a finite lifetime. The moment you say the level has a finite lifetime, that means we are quickly referred to the Heisenberg's uncertainty principle, which says that whenever there is an uncertainty in time, there is a corresponding uncertainty in energy as well. And therefore, these energy levels cannot be a straight line, a single energy value, but they have to be broadened. This is called natural broadening. We do not consider a single atom for inversion. There would be a group of atoms, so there could be collisional broadening also. They are at a particular temperature, and therefore there would be Doppler broadening as well. And therefore, this broadening of energy levels is an overall result of these all broadening processes, and therefore the energy levels actually look like this. And when we say that we have created inversion in a medium, then we do not create inversion on one particular frequency, but this gain or inversion that we have created is spread over number of frequencies. And however, the probability of emission is the highest at the line center frequency. Okay, so now tell me, do you think that lasing would happen on all these frequencies? Once again, the answer is a very strict no. Why? Because we have a cavity, and the cavity supports oscillation only on the cavity modes, and therefore the lasing can happen only on certain cavity mode frequencies. Do we have lasing on all the cavity mode frequencies? Well, and again, you have to look at this cavity a little more deeply. We have created a gain which looks like this, but we have also created a loss in the form of a transmitting mirror, and therefore this loss also has to be accounted for, and this loss is independent of frequency, so we can show it as a straight line parallel to the frequency axis. And now you can easily understand that only those cavity mode frequencies which have a net effective gain, that is, which have gain above loss, only those can laze. So in this case, there are about 5, and therefore emission of this laser may look somewhat like this. Are you disappointed that it is not very pure? Yes, it is not indeed very pure, and you can make it purer by actually reducing the broadening of the gain, so that there is only one cavity mode under the gain curve, so that lasing can take place only on that particular frequency. Or you can also reduce the length of the cavity so that you can push the cavity modes away, so that once again there is only one cavity mode under the gain curve, and you can have lasing on a single frequency. But you will appreciate, but by both these techniques, the output power that you can achieve is going to be less, because reducing the broadening will mean number of the density of these species, atomic species, is being reduced. By reducing the length of the cavity, you're actually reducing the length of the active medium, so the output that you can get will reduce. So there is another method by which you can make the emission pure. You all know of dispersive element like a prism or a grating. So what does it do? It actually separates out the various frequencies when light passes through it. So we make use of an intracavity prism or a grating, and the cavity modes, as they pass through it, because they're different frequencies, they will be dispersed, and we provide feedback only to one of them, so that it falls normally in the output mirror, and it gets feedback inside the cavity while others are thrown out of the cavity. So in this way, the emission of this particular laser can be made extremely pure. A cavity, therefore, not only increases the interaction of the photons with the inverted medium, it also makes the emission much more monochromatic. At this point, I would like to digress a little and say that the very first laser that was demonstrated by Maiman in 1960 did not make use of a cavity. So then what was it that made him feel and so very categorically say that what he observed is actually light amplification by stimulated emission alone? Let us consider his experiment. You know, his experiment is a little simple in the sense, I mean, it has just few figures and some text. It was as if he was in a great hurry to finish off the experiment and communicate the results. Understandably, because probably at that particular time, there was a lot of competition and a lot of hard work and research going on into the operation of the first laser. So his work he sent to the most prestigious physics journals, that was physical review letters, which however somehow did not strike a chord with the editor, who returned it back saying that the results were scanty, much to the advantage and benefit of Nature, which immediately published it. And you know, the rest is history. So what is the experiment? He made use of a cylindrical ruby rod, which was optically pumped by means of a flash lamp surrounding it. And he collected the light. You know, when you pump, there would be excited atoms, so they would fluoresce. So he collected the light from the ruby rod, and he measured the intensity as a function of wavelength. Okay, so in the first case, he pumped it very soft, in the sense that the number of atoms in the excited level was smaller. So what he found was the emission width was similar to how a ruby would normally fluoresce. In the second experiment, he increased the rate of pumping so that the number of excited species increases. And the measured light emitted by this fluorescent ruby rod was somewhat like this, which shows that yes, the intensity has increased, but the spectral width remains the same. And in the third case, he pumped it very hard. The rate of pumping was so hard that the population inversion took place, and the population in the excited level far exceeded that in the lower level. And he observed a dramatic decrease in the spectral width, the emission width of the light that is obtained from here. And he said that this spectral narrowing is indeed the signature of amplification of light by stimulated emission of radiation. You probably now understand how there is a spectral narrowing, right? Because we have already spoken, we've already talked about the characteristics of stimulated emission. But let me just tell for the benefit of you once again. You see, suppose this is the ruby rod where we have created population inversion. And initially, the spontaneous emission has such a width. We know it cannot be in a single frequency, so there is a width. And the number of photons emitted at the line center frequency, mu naught, is the maximum. Now, this mu naught, as this photons at mu naught, which is at a higher number, as it travels through the ruby rod, they encounter population in the excited level. They cause stimulated emission more as compared to those in the wings. Correct, because you already have higher number of photons in this mu naught region. So they will cause more stimulated emission, thereby producing more photons at mu naught frequency, which will further again cause more stimulated emission. So this is a regenerative process. And as this packet goes through the ruby rod, the spectral width becomes much narrow, and the number of photons at the line center frequency increases beyond much more beyond those at the wings. And therefore there is a definite spectral narrowing, which is the signature of light amplification by stimulated emission of radiation. So having come this far, we now by ourselves can tell what are the properties of a laser emission. You would easily be able to understand why these are the properties of a laser emission. First of all, monochromaticity. The narrowness of emission width as compared to spontaneous emission is because of stimulated emission process. The low divergence, you see, we have a very high directionality as a result of stimulated emission, and by having a cavity, you're actually making it more directional, much more monochromatic and much more directional as well. And coherence is actually something which is dependent on these two properties, but we can describe it in the following manner. If there exists a definite phase relationship between the radiation emitted by the source and observed at a point P at a time t and at a time later time t plus tau, then we say that this source is temporally coherent over this time tau. Similarly, if there exists a definite phase relationship between the radiation that is emitted from 2 points of the same source, then we say that it is spatially coherent. And knowing the properties of monochromaticity and divergence, we know that a laser source would definitely be both spatially and temporally coherent, much more than an ordinary conventional source of light. Having come this far, let us just briefly try to see and learn a little about the levels that participate in the process of lasing. Let us consider a two-level system. So to create inversion, our main aim is to create inversion, and therefore we have to take more than 50% of the population from the source to the higher level. Now, the moment the two levels have equal population, then the coming photon, the probability for it to interact with an upper excited atom and bring it down, giving rise to stimulated emission, or to interact with a atom in the ground state, getting absorbed and going up, it becomes same. And therefore, no further inversion is possible, and therefore lasing in a two-level system is not observed. In case of a three-level system, on the other hand, the population is taken from the source level to an upper level, which is not to a pump level, which is different from the upper level. And the population from here is quickly connected by means of fast relaxation, non-radiative relaxation to this upper level. And therefore, inversion needs to be created between these two levels. And although 50% of the population still has to go here, but there is no restriction on the rate of pumping from here to here, because this is practically empty. All the population which goes here is quickly communicated here. And therefore, although not very efficient, lasers of this kind do exist, and Ruby laser, for that matter, is a three-level system. The four-level system is the most efficient one, where the upper and lower levels are totally disconnected from the source and the pump level. So population is taken from the source level to a pump level, which is connected through fast relaxation to the upper level. So assuming that this lower level is a little far from the source level, we can assume that there is no population here, and therefore, technically speaking, even if you take one atom from here to here, you have created inversion. But normally there is some thermal population. However, creating inversion here in a four-level system is much, much easier, and therefore almost all efficient lasers you name, for example, Nd:YAG laser, fiber laser, CO2 laser, dye laser, they all belong to some kind of a four-level system only. Please observe that while we are giving an energy of this kind, you get an energy output of this kind. This is called quantum efficiency, and it is not 100%. Moreover, there are other losses also in a laser. So the difference in the energy of what is supplied and what we get out, that actually remains in the lasing system, and therefore it gets heated up, and cooling is an essential requirement to make the laser operate efficiently. By giving a continuous pumping, you can get a continuous output, and therefore the laser can be operated in a continuous mode, although the achievable power output is restricted by the accumulation of heat, leading to the reduction of population inversion. But by concentrating the pump energy in time, a laser can be pulsed, and the peak power can be greatly increased. Like Madam was saying, that by making use of special techniques, you can have Q switching, cavity dumping, amplification, chirped pulse amplification, by which giant pulses of very short duration can be created. And such giant pulses have very many special applications in fusion, you name many different applications, and these are actually made, such pulsing has become a very topical area of work of late. Yeah, so now we have lasers spanning over almost the entire electromagnetic spectrum. Infrared lasers working in the mid-infrared, far infrared regions like CO2, CO, YAG, fiber, etc. We have in the visible region dye, copper vapor, diode, etc. And you also have in the UV region like excimer, nitrogen, all these lasers. However, there is lot of gap in between, and many a times you require lasers, you want coherent sources in this region as well. Now, with the advent of laser, a very new area of optics came into existence, and that is the nonlinear optics. And nonlinear optics in turn has served lasers by being able to provide some new coherent sources in the intermediate gaps. You know, the polarization of a medium is actually proportional to the electric field that is incident on it because of the laser light, because of the light, any light. Yeah, and this depends on the susceptibility, and the magnitude of this depends on the susceptibility. But whatever I showed just now is an incomplete equation. Actually, there are many higher powers of electric field. Infinite, it is an infinite Taylor species equation where you have higher powers of electric field as well. But these are disregarded, or we neglect them because their magnitude is much lower as compared to the first term. These susceptibilities are also much smaller, and therefore we generally consider the first term and we say that P is proportional to E. But with the advent of high intensity lasers, this high intensity which is associated with the laser beam can exploit this nonlinear dependence of polarization on electric field and change the frequency of the incident light in certain special crystals called birefringent crystals into other frequencies. I'll just explain very briefly. You know what birefringence is. You know, when the electric field that is associated with light, you can resolve it into the two normal components, the parallel and the perpendicular, with respect to the angle of the plane of incidence. Now, for certain crystals, these two components of polarization have different, they see different refractive indices in some particular directions, and therefore the speeds are different. And this allows us to realize the possibility of frequency doubling, tripling some frequency generations. So actually you can have two photons fuse into one to give double the frequency. So in this case, the speed of light with frequency omega and that with frequency 2 omega is same in some particular direction, and therefore there can be exchange of energy between these two beams, and one grows at the expense of the other. Similarly, you can split one into two, and therefore you can have from 2 omega you can generate a coherent light of frequency omega. And birefringence is what of these crystals, some special nonlinear crystals, that makes this possible. So this is one beautiful picture where you see the red light is actually converted into its second harmonic 2 omega by going through a nonlinear crystal in the visible region. Now, with so many unique properties of laser that we have seen, monochromaticity, coherence, all this, laser naturally has very wide applications in diverse areas. Medicine, manufacturing, nuclear industry, communication, defense, you name, and laser has made its mark in all those particular fields. I will just touch upon very few. The first is laser, you know, has become now commonplace in material processing. By tailoring the properties of a laser, you can make it do cutting, drilling, welding, surface hardening, marking, whatever you name, and laser is there to do it for you. In nuclear industry, where we have radioactive contamination, usage of lasers has a very special appeal. Why? Because it comes with the possibility of remote operation, and therefore that leads to less exposure to the personnel who are handling the activity, and also it leads to the possibility of generation of very little secondary waste, and therefore lasers are used in nuclear industry for cutting of fuel bundles, welding, marking, decontamination of radioactive surfaces, etc. I will just touch upon the last one. You know, when the fuel pellets are loaded into the fuel tube, then the outer surface of the fuel tube is contaminated by the powdery fuel contamination, and this has to be first cleaned before this nuclear fuel element can actually be taken for assembly. This contamination is loosely bound to the clad surface, and therefore manual and ultrasonic methods are generally used. But manual method, as I have already said, it increases the risk to the person because they are exposed, and ultrasonic method gives rise to large amount of liquid waste which again has to be safely disposed of. So we have been able to use laser very effectively to clean this contamination. You know, just the thermal stress that is imparted to the particles due to the exposure to the laser beam of right parameters is enough to remove this powdery contamination, while leaving the surface underneath totally unscathed, totally unaffected. This is the most important condition, because these fuel elements will actually go into the hostile environment of a reactor, and therefore the surface properties should not be altered at all. For example, the corrosion resistance or the strength, and therefore by tailoring the properties, we were able to achieve this, and this now is being routinely used in our fuel fabrication centers. Laser is used in science and research. We know laser spectroscopy is like vibrational spectroscopy, atomic spectroscopy and all is very well known. You know, femtosecond pulses are created, and femtosecond chemistry is now a very evolving chemistry, where actually you can have a running commentary of a chemical reaction by making use of femtosecond pulses, right from the time the reactants are clubbed to the time the products are formed. So very exciting research with lasers is possible. But I would like to tell you a very simple experiment that we all do in our undergraduate classes, and you all must have done or must be doing, and it is a Michaelson-Morley experiment. You see, the setup is somewhat like this. The source, the beam from the source is bifurcated into two parts. One goes on to a movable mirror and the other goes to a fixed mirror. These two are again combined, the reflections from these mirrors is combined, and the fringes are observed on a screen. The most important criteria to observe contrasting fringes is that the length of these two fringes, of these two limbs, paths, should be as equal as possible. That means we want that the light should travel for the same time between these two paths. That means we want that the light should emerge from the source at the same time. That means we want the beams to be temporally coherent. Then the source should be apertured down as much as possible. Why? Because we want that the light should emerge from the same point of the source. That is, we want spatial coherence. Normally we use sodium vapor lamp in our laboratory. Now I don't know, maybe you're using a helium neon, I'm not sure. But this coherence length, which is a measure of temporal coherence, is about 1 centimeter for sodium vapor lamp. It could be tens of centimeters for commercial helium neon, and it can go into kilometers for a highly stabilized helium neon laser. And therefore, when such a movable mirror can be actually placed on the wall of a dam or an earthquake prone region, and any change or any movement in that particular place can be observed as movement of the fringes in the laboratory itself, and that can serve as an advance warning of earthquake, flood, volcanic activity, etc. Now, lasers in medicine is almost as old as the laser itself, because in early 60s itself, a pulsed ruby laser was made use of to treat retinal detachment. This is a condition where the retina of the eye has a tear, or it is slightly detached from the underlying tissue, and therefore this almost renders the person blind. But with the laser, the cure is not only total but almost instantaneous. It only needs an intense pulse, which actually burns the tissue, underlying tissue, allowing a scar tissue to grow, and therefore fuses the retina to the underlying tissue. Bloodless surgery, where laser acts as a knife of light that works simultaneously as both cutting and coagulation tool. You see, mid-infrared laser, for example, a CO2 laser, has a very strong absorption in the water that lies in our tissue and can instantaneously vaporize it, creating a very fine cut. But when there is a cut, blood vessels open up and therefore blood starts oozing out. By tailoring the parameters of the laser, the right temperature can also be reached so that these blood vessels are coagulated, sealed immediately, so that you can have a cut, but there is no bleeding. So this assumes importance in surgeries of highly vascular regions like liver, etc., where the doctors are primarily worried about blood loss more than probably the intricacy of the surgery itself. Laser can also be used for treating cancers. Laser can reach the tumor directly or through an optical fiber, and heat up the cancerous cell and destroy. It can be used for early detection of malignancy. The laser is shown on the required body part. The fluorescence emitted from that body part is compared with that of the natural tissue, and any deviation can give an indication about the probability of onset of malignancy. Targeted drug delivery is one very promising and currently hot research topic, where laser can be used as a tweezer to just pick a micro drug and place it on the malignant cell. So this way it can be highly targeted, and it can make this chemotherapy, you know, chemotherapy is so dreaded now because of the side effects. So it can make this chemotherapy a very, very highly effective one. Laser angioplasty, where the heart artery blockage is removed through the process of laser ablation. This now has become a very commonplace. Laser is also used to measure the distance between two objects, and the method is just the time of flight technique, where a short laser pulse is shown on to the object, and the reflected light is collected, and the time taken for this, from that you can estimate the distance between the two objects. In fact, the distance between Earth and Moon was actually measured by making use of a laser, by making use of a reflector that has been placed on the Moon in one of the lunar missions. And the distance between Earth and Moon was measured to an incredible accuracy of almost 2 centimeters. Lasers in defense, the moment you talk of lasers in defense, we remember all those sci-fi movies where laser beams are shown and then it vaporizes the enemy target or enemy aeroplane. And this was actually taken very seriously by America during the Cold War regime, when the ties were very hostile between erstwhile USSR and USA, in their strategic defense initiative, where they had an ambitious plan to shield their entire territory by placing powerful lasers at strategically located orbits. Their idea was to destroy the warhead in the country of origin itself. So laser can be used to guide a missile. That is, the infrared beam from the laser can actually be scattered from a fixed target, and this acts as a guide for another conventional missile to give it a very precision hit. Laser can also be used as a weapon to destroy a fast moving object in air, because when compared to the speed of light, the moving object would actually appear frozen. Now, laser has now entered into the cosmetic industry as well, because lasers can resurfacing is being used for removing wrinkles, scars, blemishes, etc. Laser is also in a big way into the fashion industry, where intricate, elegant, classical patterns can be ornamented onto clothing of all kinds of fabrics. And this is revolutionizing the fashion industry. How is this possible? You know, the very small divergence of the laser beam allows it to be focused to a very tiny spot, less than probably the thickness of the hair itself. And therefore, very intricate patterns can be created on the fabric, and probably cannot be copied even. So that's how laser can be used even in fashion industry. There are many, many more applications, but I think I don't know if I have exceeded my time. So I think I'll stop here, and thank you all for your kind attention. And I wish that I have been able to make you understand at least a little in terms of laser, its fundamentals, and how exciting and beautiful this particular invention and instrument is. Thank you. Hello. Hello.
Thank you, ma'am.
Yeah.
Hello. Thank you, ma'am.
Madam, how much time did I take?
No, ma'am, it's all you are on time, sir, ma'am.
Okay.
So
okay.
thank you, ma'am.
Yeah.
Participants, kindly drop your questions in the chat box. Ma'am, there is a question from a participant.
Yeah.
Why can we not increase the loose line, that is decrease the reflectivity of the S2 mirror, and thus reducing the number of standing modes to make the laser pure? Why can we not increase the loose line? It is there in the chat box, ma'am. Why can we not increase the loose line and thus reducing the number of standing modes
Madam, the number of wavelength which would be resonant to a particular cavity will be dependent on the length of the cavity. N lambda by 2 is equal to L. That is how it is. By reducing the reflectivity of the output mirror, which the student is saying, we can actually couple out more, but that will also increase the loss of the cavity. So the moment you increase, see, there is a real balance between the intracavity flux and what can be coupled out. The moment we try to reduce the reflectivity of the output mirror, our loss increases, and therefore the loss line goes up, right? So it is possible that we may have to create a lot of inversion. See, to get an output, you have to create inversion. So by increasing the loss that way, our pumping has to be much more effective. So basically, for a particular resonator cavity and for a particular type of laser that we are operating, a particular reflectivity is the most optimum. Okay, so below that reflectivity, you can actually you can try to increase the output by increasing the reflectivity, but after a particular point, this loss, the increased reflectivity will actually mean that you are putting more photons inside the cavity, not allowing them to come out. So that way there is a compromise, and a particular reflectivity is the most optimum for a given cavity.
Okay. Thank you, ma'am.
Yeah.
There is one more question.
Yes, ma'am.
Laser use a measure instrument for ice thickness or densities?
Pardon? Ice thickness?
Can laser, yes.
Yes,
ice thickness.
Oh, definitely.
Yes.
It can be used for measuring the thickness. Actually, I think my colleague who will be going to talk will in the next thing, he will be able to tell how laser is actually used to measure. He will be talking about laser-based instrumentation, and he will say how laser can be used to measure the thicknesses or the velocities, etc. Yes, it can be used for measuring the thickness of any object. That is possible. Yeah.
And one more question. What are the nonlinear applications of laser?
Nonlinear applications. Yeah, like as I said, one of the most important is you generate many more coherent sources by making use of these nonlinear processes. For example, some frequency, difference frequency, you can generate a whole new set of wavelengths. There is optical, there is something called OPO, optical parametric oscillator, which can be formed, where you can generate a continuous, you can generate a source where you can have output coming almost continuously by changing the angle of the nonlinear crystal, or by changing the angle of incidence, or changing the temperature of the crystal. So nonlinear optics has now given us a way of generating many more sources in this particular region. And apart from this, I'm sure this nonlinear optics is a big branch in itself, and it would help us reveal the so many nonlinear interactions that are possible in matter by making use of lasers.
So one question, very simple question. What do you mean by nonlinear?
Yeah, I just said that when we said anything that is not linear is non-linear. Yes. So as I said, the polarization, when the light has an electric field component associated with it. So when light is incident on a surface, it induces polarization inside the atoms or molecules where it is falling on. So this polarization is proportional to, we have written electric field to the first power, but actually it is not proportional to the first power alone. It has many more higher orders. So it is actually chi 0 E plus chi 1 E square plus chi, so it is actually it is a Taylor's expansion which goes into infinity. So all these other orders apart from that first one, proportionality to E alone, this is a nonlinear equation. And any effect which makes use of these higher orders, for example, we say second harmonic generation makes use of E square property, or there is some other there is something else which will make of the EQ property. So this is the nonlinear aspect of polarization here. That is what I have told about nonlinear optics.
Thank you, ma'am.
Yeah.
Thank you. Hopefully all the participants, they have cleared their doubts. So we are really thankful to you, ma'am.
Actually, I can share my email address. You have my email address. So in case any participant wants to write to me, they can write as well.
Okay, okay.
Yeah.
So
Thank
there
you
is
very
one more question again. And lasers are not hazardous to our body.
Yes, yes. See, laser,
Yes.
because of its such high brightness and intensity that is possible with a laser, they can definitely harm us if we are not careful. So when we operate a laser, special precautions have to be taken. You see, when we say that laser is going and destroying a cancerous cell, or it is destroying, it is welding a retina in the eye. So if you look at it directly, then it can create a lot of problem, right? So every laser comes with its own safety aspect. While making a laser, you may be operating with high voltage, etc. So that is another set of precautions that need to be taken. And apart from that, a laser, depending on the wavelength that it is emitting, depending on the power, intensity, brightness, and depending on the absorption that it will have in different body parts, precautions have to be taken.
Thank you, ma'am.
Yeah.
Thank you, ma'am. Your session was very informative, elaborative, well explained, and very much interactive. So, ma'am, I'm sure BSc, MSc students, research scholars, and faculty members of various institutions. So, thank you once again, ma'am.
Yeah. Thank you. It was
We are really privileged to have you in our workshop. So now, quickly, I'll request one more, the second session of our workshop. So the second session of our workshop, the invited resource person is Sri Asim Singh Rawat. So, sir, you are ready, sir?
Yes.
Okay, thank you, sir. So now I request, sir, your presentations and all everything is ready?
just a second.
Yes.
Okay. So Sri Asim Singh Rawat, he is a graduate in electronic engineering from SITS Devi Ahalya University, Indore. He did his MTech in electrical engineering with specialization in electronic systems from IIT Mumbai. He is working in Laser and Plasma Technology Division of Bhabha Atomic Research Center, BARC, since 1993 on laser-based instrumentations. He has worked on the development of laser-based diameter measuring instruments like Laskin diagos, surface roughness measuring instruments like laser surface check, projectile velocity measuring instruments, laser screen projectile velocimeter, vibration measuring instruments like Kampan, and particle image velocimeter system for flow visualization. The technology of Laskin diagos has been transferred to 5 private industries. The technology of laser screen projectile velocimeter and Kampan has also been transferred to private industries. He has so far authored 21 papers and more than 2 bar technical reports on laser-based instrumentation. He received Department of Atomic Energy Scientific and Technical Excellence Award in the year 2012. Presently, he is working on laser-based perimeter intrusion detection system, expansion rate measurement system, opacity monitor, and photon Doppler velocimeter. So we are really privileged to have you, sir, in this in our second session. Now I request, sir. Sir is serving as a scientific officer, H Laser and Plasma Technology Division, Bar. Currently his position. So now I request, sir, kindly take over the session.
Full screen, full screen, full screen.
Good afternoon to everyone. Am I audible? Is it okay, madam?
Yes, sir. Yes, sir. You are audible, sir.
Good afternoon, everyone. First of all, I would like to thank Indian Women Scientists Association and Indian Academy of Degree College to give me this opportunity to speak on this subject of laser-based instrumentation. As in my previous talk, Dr. Padma has talked about the basic concepts of laser and various applications of laser. So laser-based instrumentation is one of the important application of laser because of the special properties of laser, and it is widely being used nowadays. So first of all, I would talk about some of the relevant terminologies used in the field of laser-based instrumentation. The laser, as it has already been told, is a acronym of light amplification by stimulated emission of radiation. Now the instrument, what we understand with the instrument is that there are different types of instrument. There could be some musical instrument also, but here we are referring to the instrument, which is a device for determining the value or magnitude of a parameter or variable. That is, it performs measurement. So it is a measuring instrument which we are talking. Then instrumentation is an art or technology of design, development, operation, maintenance of such measuring instruments. So the laser-based instrumentation is a field which consists of design, development, operation, maintenance of measuring instrument in which laser becomes an integral part of the sensor. So this makes an instrument non-contact, non-destructive, and fast in nature. Thus, the laser-based instrumentation are useful for remote measurement in toxic and hazardous environment, as a contact type of instrument will have the problems of getting contaminated or getting some problems. So for online process monitoring and for toxic and hazardous environment, laser-based instruments has a special significance apart from routine measurements. So the important properties of laser which are useful in development of a laser-based instruments are spatial coherence and the temporal coherence. As it is explained in previous lecture, what is spatial coherence? The spatial coherence is the phase uniformity between the 2 points in the wavefront. Because of this property, we get a collimated beam, high intense beam, and fine narrow beam of laser beam, and which can be focused to a sharp spot. That makes the measurement very easy and possible in many applications. Similarly, there is temporal coherence, which is the phase uniformity with time, and this leads to the monochromicity of a laser beam. Monochromicity means single color, single wavelength of the laser beam, and because of this single wavelength of the laser beam, there are phenomena called interference which can take place between two beams of a laser, single laser beam, and because of this interference we are able to measure many parameters to a very fine accuracy of wavelength level, like nanometer or sub-nanometer level of measurement. Now, the most important laser which is used in laser-based instrumentation is diode laser. Why? Because diode laser is a very compact, low cost, low power requirement, and compact device. So because of the diode laser, and it carries all the properties of a laser beam, which is spatial and temporal coherence. So because of the availability of cheap and low cost and compact diode laser and operating in low power, the field of instrumentation has found large number of applications. The diode laser, the properties of diode laser which are mostly used in instrumentation are the wavelength, as it is available in different wavelength. Most of the lasers are mostly available in a narrow band of wavelength only, but diode laser has a property by modifying its content, its constituent material, we can get different wavelengths in the diode laser. So the most commonly wavelengths available for diode laser are 635 nanometer, 670 nanometer, and 1550 nanometer. 635 and 670 are visible red wavelengths, while 1550 is infrared wavelength, which is mostly used in communication application, and also in instrumentation it has now been used. Then the output power of the diode laser is in few milliwatt, which is what is the requirement in measurement application. So one need not to use a very high power and high wattage laser for measurement application. So milliwatt power is required, so it required low in electrical power also, and it makes the thing laser diode compact also. And the laser diode can be used in continuous wave mode or in pulse mode, as it has the facility of modulating its intensity with different rate. So it can be used in the laser diode can be operated in continuous wave mode or in pulse mode. Then the beam divergence of laser diode is also very small, 0.2 millirad. So we can do the measurement at a long distance using laser beam. Then current drawn by the laser diode is 50 milliampere or so, 100 less than 100 milliampere. So again, required low electrical power to operate. Voltage input is 4 to 6.5 volt. TTL input can be used for operating a laser diode. It has a beam dimension in rectangular in shape normally, which is 3 mm to 2.8 mm, but it can be reduced to a circular beam by using diffractive special optics, and 1 mm beam of circular nature can be obtained using laser diode. Then we can modulate it in kilohertz to megahertz. That is what I told you. The material which is used for making a diode laser is indium gallium aluminum phosphorus, which is used to make a visible laser diode of 635 670 nanometer, while gallium aluminum arsenide is used for making infrared laser diode at 980 or 1550 nanometer. It has a safety rating of 3A or 2, which is because 5 milliwatt kind of power we are using. Then the mechanical dimension of a laser diode is length is say 90 mm and diameter is 23 mm. So kind of pen size of dimension we get in using this laser. The laser diode is used in the module form. So it has a laser diode chip, which in front of which we put a proper collimating optics to get a collimated beam of light. And this optics can make it circular, or a line can be generated, or a expanded beam can be generated. And in the same module, we have a driver electronics also, so that externally we need to only supply a constant DC voltage of 5 volt, while the driver electronics takes care of all the requirement of operating the laser diode, like soft start, soft stop, spike protection, as laser diode is very sensitive to spikes in the current or voltage. So all these precautions are required in the driver circuit of the laser diode, which is incorporated in the module. So the use of module for making an instrument becomes very handy, and relieve the user from all the botheration of precautions and the collimating optics requirement. And it can be very small also. Like I told, the length of 190 mm and diameter of 23 mm is used. Now I'll just briefly tell you about the general concept of block diagram of a laser-based instrument. A laser-based instrument normally consists of a laser source, which is in most of the cases a diode laser. Then there is a beam shaping optics according to the requirement of the measurement. The beam shaping optics could be a beam circularizer, it could be line generating optics, it could be a beam expander, it could be a ring formation. So the particular beam shaping optics is kept in the front of the laser source to generate particular shape of beam, which then interact with the object whose parameter has to be measured, whether its diameter is to be measured, surface roughness is to be measured, or vibration is to be measured. Whatever parameter of the object is to be measured, the beam then interact with the object. Then the backscattered light or the transmitted light or reflected light from the object is then collected by light collecting optics, which then focuses this collected light onto a photodetector. The output of the photodetector is a current signal, which is processed by the processing electronics, and the computation circuit is there, like microcontroller or PC, which based on the signal characteristic, it determines the parameter or the object variable which is to be determined, and displays and give to the user in the form of user interface through a screen or kind of thing. So this is the general arrangement used in developing a laser-based instrument. Now I will discuss some of the optical techniques which are used for measurement of different parameters. First is the shadow pulse technique. This shadow pulse technique is used. We have used this shadow pulse technique for measuring the diameter of an object, non-contact measure based on non-contact technique. Then another second technique I will be discussing, optical triangulation technique. in which distance or displacement of an object from a particular standard of distance or vibration of an object can be measured remotely. Then third technique I will be discussing is time of flight, in which either the time between the two events is variable and the distance is fixed, so we measure the time, or if the time between the two events is known, then the distance between the two events is measured, and using d by t ratio, simple, we can find the velocity of the object. So for this, I'll be explaining the projectile speed measurement instrument which we have developed, and then flow visualization for measuring the velocity of a liquid flow. Then specular reflection technique I'll be discussing for roughness measurement of a surface using laser beam. So first is pulse shadow measurement based diameter measurement. So here what happens, laser beam from a diode laser is made to fall on a scanning mirror which is mounted on the shaft of a DC motor. So this mirror, when rotates, when the motor is running, the mirror rotates. With the rotation of mirror, the beam falling on the mirror gets reflected in different direction. So it reflects in a different direction in the vertical plane, as the mirror is mounted horizontally. So it reflects in vertical plane from this place to this place. Thus, it scans the vertical plane of the object of the paper. Now, this point of reflection is at the focal point of this lens. We are keeping the reflecting point of the mirror at the focal point of this lens. Now, you must have read that any beam coming from the focal point of a lens gets collimated or become horizontal after passing through the lens. So that is what the property we are using. So all the reflected beam which are coming from the mirror are, after passing through the lens, becomes parallel. Now these parallel beams are scanning the vertical plane. Now if these parallel beams, after traveling some distance, another lens is used to focus this beam onto a photodiode. Now as the mirror is rotating, the beam travels from top to bottom. As the initially beam is allowed to pass through this, the beam is falling on the photodiode, which give rise to the higher voltage on the output of the photodiode. But when the object is kept perpendicular plane of the paper at the center of it, the beam scanning through this region of the plane will get obstructed by the object. When it is obstructed, there is no beam falling on the photodiode. So the output of the photodiode goes low. So this is the shadow which is generated by the object. So this shadow, width of this shadow is gives the time duration for which the beam is obstructed by the object. Again, when the beam crosses the object, goes below this, the output of the photodiode becomes high as the beam starts falling on the photodiode. So then when the beam completes its scanning, the output again goes low. So the total time T is the time taken by the beam to scan from top to bottom, and small t is the time taken by the beam to scan the diameter of the object. So if we take the ratio of these two, T by T, and multiply it with the aperture, we get the diameter of the object. This diameter is this time, small time and capital T and small t are measured by a counter, in high-speed counter in the logic circuit, and a microcontroller based circuit calculates the diameter using this formula, and it is display on the LCD display, and a keyboard is provided. So we have developed this instrument, and now I can show you the instrument which we have developed. So this is the instrument in which this is the object which we are keeping on the V mount, and laser beam is scanning vertical plane is mounted here, and here all microcontroller based circuit is there, and this display is there to display the diameter value. It has the specification. If you see, it has the measuring range of 1 mm to 25 mm. It can measure the diameter with an accuracy of ±5 micron, and has the repeatability of ±1 micron. The laser spot size which we are keeping at the plane of the object is 0.5 mm. It scans the plane or object at the rate of 25 revolutions per second, is the rotation rate. So 25 times it takes the reading and take the average of that. And so one reading takes around less than 1 second. Then we have provided a software facility to the screen, touch screen, that this can be used for measuring the diameter. At the same time, if one is not interested in actual diameter and one only wants to sort out specified diameters of samples within a given lot of samples, so we can set the lower and higher limit in the software within a interval of 100 micron, and whatever it will, you can just keep it and it will display the measured diameter is within the given range, acceptable range, lower than that or higher than that. So there is no need of directly measuring the full diameter, exact diameter, and we can just sort out the sample of diameters of within a given range. The technology of this instrument we have already transferred to some private industries. Now the next technique which I'm talking about is optical triangulation technique. This technique is used for measuring the distance or displacement of an object from our source. So this can also be used for measuring the vibration of an object, non-contact vibration measured from a distance. So it is based on triangle which is found between the light source, the point of reflection of the object, and the detector. So geometry of triangle is used to calculate the position of the object and its displacement from its standoff location, and the variation of the focus spot on the detector gives the surface displacement. So this, the general schematic of this, there are two techniques by which we can make the light beam fall on the surface. One is when the light beam falls perpendicular to the surface. So backscattered light is collected by a lens which is obliquely placed with respect to surface, and the backscattered light is focused on a position sensitive detector. So a displacement of delta of the object results in displacement of small delta on the position sensitive detector, and the relationship between this delta and this delta is given by m into sine theta upon sine phi into capital delta. So this sine theta is the angle between the reflected beam, optical axis of the lens, and the laser beam, and phi is the angle between the optical axis of the lens and plane of the detector. So, and m is the magnification of the lens, which is object distance upon image distance upon object distance. So this is the one technique. The another technique which we use for developing the displacement measurement is in which we are making the laser beam to fall in inclined angle to the surface, and perpendicular to the surface we are keeping our optical axis and the lens which is collecting the light beam and focusing on the position. The advantage of this technique over the previous technique is that here we get better linearity and more equal for short range of displacement. The linearity is better in this case and more resolution, more accuracy. So here the angle of beam is falling at an angle of oblique angle to the surface, normal to the surface, and normal to the surface is aligned with the optical axis of the lens. So the scattered light is collected by the lens and focused on the position sensitive detector. So when the target moves at distance delta towards the or away from the detector, it results in displacement of the focus spot on the detector by a distance small delta. So the displacement of the focus spot on the detector is measured, calculated using the difference and amplifier circuit and divider circuit, which works on the principle that the position of the focus spot is given by x by 2 a minus b upon a plus b, where a and b are the voltages at the output of one end of the output, and b is the voltage at another end of the detector, and x is the total length of the position sensitive detector. So this way we can find out the position of the focus spot on this, And once this focus position on the focus portion of the focus spot on the detector is determined, you can calculate delta, which is displacement of the target, using this formula. Delta is LO delta upon Li tan theta plus delta. Now, to make the things more linear and more easy, we this tan theta is the angle between the light beam and the normal to the surface, this theta, and phi is, as I explained, is the angle between the detector and the optical axis. Now here we have kept phi as 90 degree. So that term goes away from the formula. Now this theta is kept at 45 degree because we are keeping this distance and this distance equal. So if we keep this theta is 45 degree, this becomes 1. And if Li is taken as LO, this the distance of the target from the lens and distance of the detector from the lens are kept equal, Li and LO. So we see that if Li is equal to LO and theta is 45 and Li is very higher than delta, this can be neglected. So delta becomes delta, small delta becomes capital delta. So whatever is the displacement of target is exactly same as the displacement of the focus spot on the PSD. So by measuring the displacement of the focus spot on the PSD, we are able to find out the displacement of the target. And for making this use of Li and LO equal, we are keeping image distance and object distance of the lens at 200 mm, and by using the focal length of the lens 100 mm. So by using the lens with focal length of 100 mm and keeping the target at 200 mm, we are getting the image at a distance of 200 mm. So the distance between the lens and the detector is 200 mm, and the standoff distance of the target from the lens is 200 mm. So we are able to measure the displacement and vibration of the object from a distance of 200 mm. That is what we, this is the instrument which we have developed, and its technology is also transferred. So here we are, here is the laser diode, which the beam is falling oblique to the normal to the surface. And here is the lens, which is collecting the backscattered light and focusing on a PSD. And this output of this is interfaced to a PC, in which the frequency spectrum of the signal and the time domain signal is displayed for the user interface. So this is the specification of the instrument which we have developed. So it is based on optical triangulation principle, and the vibration frequency range is 0.1 hertz to 1 kilohertz we are able to measure, while the vibration amplitude is plus minus 2 micron to plus minus 5 mm. It can measure. The standoff distance is 200 mm, as I explained, by using the lens of 100 mm focal length and 50 mm dia. The maximum linearity error due to neglection of delta in the denominator is 2.5% of the measured value maximum. The resolution we are getting is 1 micron, and the output voltage is in the range of plus minus 5 volt. The light source which we are using is diode laser. As I told, that diode laser is the most widely used laser for instrumentation application. And to make the things compact and low power requirement, as power requirement is less than 5 milliwatt, and at 670 nanometers, so it is a red laser which we are using. And the spot diameter at the target is less than 1 mm, and the display interface is giving the time domain signal as well as the frequency spectrum of the signal. Now I will be talking about the time of flight principle used for velocity measurement. It is a very simple technique in which two light sheets are generated, and actually this was developed based on specific requirement from a defense lab, in which they wanted to measure the velocity of the projectile which is fired from a gas gun, and it used to strike the target sheet, and they wanted to study the material property of the target sheet. So and calculate the impact of the object. So this, and there are other techniques of measuring the velocity in which aluminum sheet screens are kept at two separate distance, and it is a destructive technique in which, through which, if the projectile passes, they measure the start and stop pulse and calculate the speed. While using a optical technique makes it non-destructive and at the same time more accurate. So here we have generated two optical screens, and the projectile is made to pass perpendicular to the screen before it hits the target. And when the projectile crosses the first screen, it generates a start pulse to the counter. Counter starts counting the pulse time, and when projectile crosses the second screen, it generates a stop pulse, so the counter gets stopped. So the time interval between the start pulse and stop pulse gives the time taken by the projectile to cover the known distance d. So by knowing the distance d, which is the distance between the two screens, and by measuring the time, we can calculate the velocity of the projectile. And this microcontroller calculates the velocity and displays it on PC. Now, these optical screens, how we are created, that I can show you. Again, we are using a laser diode, and as I told you, there are different optics which can be used in front of the laser diode to generate required shape of the beam. So here we are using a line generating optics. So it generates a line with a fan angle. So this line, however, since it is continuously expanding, we have kept another lens here to collimate it, to make it parallel. So this is the light sheet which we are generating between the transmitting and the receiving unit. Like here, this is the transmitting unit. This is the top view which we are seeing, and if we see from the side, this is the what we get. So this collimated line transmit from the transmitter to receiver. Here again, we are using a lens to focus this line onto photodetector. Now, when the projectile crosses it perpendicular to the plane of the paper, it obstructs the light for the time it is taking to pass through the screen. Now, during this time, the obstruction of light by the projectile causes the reduction in the intensity of light falling on the photodiode. Now, this photodiode output thus dips, and that dip is detected by the electronic circuit. It is capacitively coupled to cause the generation of the start pulse. Similarly, the same screen is kept at the other end, so which when the projectile crosses causes the generation of stop pulse. So these two pulses which are generated are measured and calculated the speed. Now this is the actual instrument which is used. Here these are the two screens, and this is the gas gun which fires a projectile which is around 4 mm, 5 mm in diameter spherical object, and and this is the actual setup in which this is the gas gun which you can see, and these are the instrument. So when the gas gun fires the projectile, it crosses the two screen, and this crossing of the screen is detected by the circuit and measures the velocity and displays it. The general specification of this instrument is that measuring range is from 0.01 to 5000 meter per second it can measure, with an accuracy of better than plus minus 2%. Measurement time is 10 milliseconds, depending on the minimum speed with which the projectile can move. Because of counter limitation, it can be increased or decreased. That is not an issue. But at present, we have kept it up to 10 milliseconds. The projectile size should be greater than just 1 mm. The projectile, this screen has the dimension of 40 mm length, and the width of this screen is 1 mm only. And the laser source again, which we used, is 670 nanometer and 5 milliwatt of power. The distance between the two screens we have kept as 100 mm is fixed distance, and sensor unit and monitor unit connected through optical. Actually, there was issue of high EMI generated electromagnetic interference because of operation of this gas gun. So they wanted the, and also there is danger. So person cannot stand here while it is operated. So we connected this transmitter unit through an optical fiber cable to the monitor unit, which is kept in the control room. So these start and stop pulse which are generated are transmitted through optical fiber cable to the control unit, and there in the monitor unit, it calculates and measures and displays the velocity. So through optical fiber cable, these units are connected to monitor unit, and it is a standalone instrument as microcontroller based circuit I have shown. And the data logging can be done on PC through serial interface. This instrument we have supplied to DMR Hyderabad, and technology also transferred to a private industry. Based on similar principle, but using a single screen, also we have developed one instrument, and that also was given to DMR. In this, instead of two screens, we are using the distance parameter from the object itself. So object of known diameter are required if an object of known diameter is to be used, and its velocity is to be determined, then this kind of instrument can be used, in which we are generating a line and keeping the line horizontal, unlike there where we are keeping the line vertical, because the projectile is moving horizontal. In this case, they wanted to measure the coefficient of restitution from the surface, and they wanted to measure what is the falling and rebound velocity of the ball, spherical metallic ball. So what we have done, like when the ball is falling and it crosses the screen, it causes the generation of a pulse at the output of amplifier circuit, which is given the proper shape of a square pulse, and counter measures the width of this pulse. So width of this pulse corresponds to the time taken by the object to cross this screen, and time taken by the object to cross this screen depends on the diameter of this object. So if we know the diameter, we measure the number of counts on the counter, and the T is the time period of the counter. So this gives us the time taken by the object to cross this screen, and D is the diameter of the object, so it gives the velocity of the falling. Similarly, if we have programmed it that if the object rebounds from the bottom, it will again cross the screen and again generates a pulse, which is converted into a square pulse, and which gives another count value, and by this rebound velocity can be determined. Now we have programmed it, its logic circuit such that after two measurement, it will get logged. So another time when the ball falls, only shadow pulse is generated, the square pulse is not generated, and the display maintains the two measured values of the falling and the rebound velocity, unless it is reset. And then when it is reset, then it is again ready for, because once the ball is made to fall, it will oscillate 2-3 times before dying down to the surface. So we have made the circuit such that it only measures twice the velocity and then it will stop. That provision is also there, that even if only you want to measure the falling velocity, then it can be configured from the key pad that it will measure only the falling velocity, even rebound velocity it will not measure. So this is the instrument which we have developed, in which this is the horizontal screen which is generated, and this is the keypad which is given, and this is the LCD display. So you can measure the velocity of free falling object at this level. At the same time, it can measure the rebound velocity, and then it will display both the values here. So this type of instrument can be used for measuring the coefficient of restitution of a target and also the quality of a ball. So this is a non-contact, non-destructive measurement, and it measures falling as well as rebound velocity of spherical object, and useful for finding material properties like coefficient of restitution or even viscosity. If we want to measure the viscosity of a liquid, we made to move a ball of known diameter and density and weight through it, and light sheet is passed through the liquid and measure the velocity with which it is moving down. This is the general specification of this instrument. Similar to that, it has the measurement range of 1 meter per second to 400 meters per second, and with an accuracy of plus minus 2% it gives. And again here we use a diode laser of 670 nanometer and 5 milliwatt power. Thickness of the sheet is 1 mm and width is 40 mm. It is again a standalone instrument based on an LCD display. Keyboard is provided on this instrument for user to select what kind of measurement it wants. It is used for resetting the instrument once a measurement is made, or entering the projectile dimension initially, as it requires the dimension of the projectile to calculate the velocity. Then function keys to select display the ratio of rebound to velocity or display the individual velocity, rebound velocity, and it also has a RS-232 interface for data logging on a PC, and it requires even less than 1 watt of power. It is means operated, and it is a standalone instrument. Now, similar to the time of flight principle, as I told you earlier, the time of flight principle can be used in two ways. Either if you know the distance between the two screens, you measure the time of flight between one screen to another screen by the projectile and calculate the velocity. Or if you generate two events in a fixed interval between, and there is fixed interval between them, and if you measure the distance level by the object during that two fixed interval, then also you can calculate the velocity of the projectile. So that second principle we are using in particle image velocity for flow visualization. So this is a flow visualization technique in a whole field measurement in a fluid or gaseous medium is done. That means in a water flow or fluid flow, if you want to measure the velocity of different parts in the flow, then we can use this technique. And it is a non-contact and non-perturbing in nature, as we are not putting any flow meter inside the fluid so that it obstructs the movement of the fluid. But in this, one thing is required, that to get the image of the fluid across a cross section, we introduce some tracer particles, very micro bubble, micro tracer particle, which does not affect the flow of the liquid. At the same time, enables the imaging of the fluid at particular cross section. It is a laser based measurement and suitable for transparent flow. Means the fluid should be transparent to the observer. Otherwise, if it is a dusty fluid or haziness is there, then it becomes difficult, because the imaging has to be done perfectly. Now, the principle used for this measurement is it illuminates a plane along the flow of direction of flow twice by a light sheet of nanosecond duration. So we use a pulse laser in this case, and pulse laser of nanosecond duration, we illuminate the flow with one pulse, and then after a fixed interval of time, we illuminate with another pulse. So for these two pulses, we capture the image of the fluid during this illumination, and we know the interval between the two pulses, and then by image analysis, we find out the movement of the tracer particle in the fluid during this interval. So we measure the distance, calculate the distance of traveling of the tracer particle during this interval, and we know the interval, so we calculate the velocity of particle at that point in this process. So by calculating this velocity of particle, we can calculate the velocity of complete cross section of different particles, because there are a large number of particles. So we can calculate of complete area, the velocity at different points simultaneously. Otherwise, there are other methods which use Doppler principle, in which the velocity of the fluid at a single point is measured. While in this method, we can calculate the velocity of different points across the cross section of the fluid simultaneously. Synchronous recording in the camera's motion of micro tracer particle is done, and image processing method is used for cross correlation or autocorrelation to determine the flow velocity. So this is the schematic of this instrument, in which first laser pulse illuminate the flow. It is converted into a light sheet by a cylindrical lens, and it illuminates the flow for nanosecond duration. But the intensity is such bright that clear image is obtained by the CCD camera. CCD camera is kept at right angle to the plane of the light sheet. Then after few microsecond or millisecond, depending on the velocity of the fluid which is to be measured, another laser pulse is made to illuminate the flow. So these two images are captured by the CCD camera. Now this CCD camera is triggered at the exact same time when the laser is triggered. So it can capture it image when it is illuminated. Now with these two images, the movement of the tracer particle from one illumination to another illumination is calculated using autocorrelation or cross correlation algorithm. If two separate images are captured, then cross correlation is used. If on the same image, two exposures are superimposed, then autocorrelation algorithm is used to calculate the movement of the tracer particle from one illumination to another illumination. Now we know the time difference between the two illumination, and now when we calculate the displacement of the target, we can calculate the velocity of that particular particle, and hence the velocity of the fluid at that point. So this is the PIV setup which we have developed in our lab, in which this is the articulated arm. So light sheet illuminates the flow, and this is the flow setup which we have made. So flow is moving in this direction, while light sheet illuminates it in vertical plane. And this is the camera. So camera captures the light plane or area which is illuminated. Now this shows the actual principle. So from with the laser beam is illuminating the flow in vertical plane, and this camera is capturing the image of the time when laser is illuminating flow. So double here I am showing the image which is double exposed by two illumination. So on the same image, 2 times the laser pulse is illuminating the flow. So the tracer particle movement from one position to another position, like this tracer particle move from here to here. So by cross correlation, autocorrelation within this image, you can find out the movement of the particle, and we know the time interval between the two light sheet of exposure, so we can calculate the velocity. This is for the dye cell. We have measured the velocity of the fluid flowing through it, and this is in a tank with a stirrer. So these are the velocity vectors which we got at different points on the flow, and this is along the length of the dye cell, and this is along the width of the dye cell. This is kind of the velocity profile that matches with the general physics principle that along the boundary the velocity is minimum, and at the center of the width of a cell we get the maximum velocity. So the velocity vector which we got is around 1 meter per second for dye cell, and for tanks we got up to 2.1 meter per second. So now the last technique which I'm going to explain is this is optical technique for measurement of roughness of a surface. So what we are doing is actually optically it is possible. The normal method used for roughness measurement is a stylus based, in which a stylus, diamond stylus, moves on the surface, and variation on the surface are recorded by the PZT connected to the stylus, and it gives the profile of the surface. And from that profile we calculate the roughness, average roughness, RMS roughness of the surface. But it is a kind of destructive technique, because the diamond tip, while traveling through the surface, also produces scratch on the surface. And also for soft and smooth surfaces, and which are costly, it is not possible to use this technique. And optical techniques are preferred in such cases. So in optical techniques, there are two types. One is profiling technique, in which the laser beam, fine spot of beam, is made to travel on the surface, and backscattered light is collected and imaged to give the actual profile of the surface. While there are parametric technique for fast and routine comparison of surfaces, in which specular reflectance is measured from the surface, or total integrated scatter is used, or diffuseness of scattered light. These three methods can be used for routine comparison of fast, to find out the average parameter of the roughness of the surface, rather than actually determine the profile of the surface. So we have worked on the specular reflectance based roughness measurement, in which the light source is made to fall at an grazing incidence angle on the surface, and the light reflected in the specular direction is collected. If it has been given that if the angle of incidence is near grazing and the roughness of the surface is less than the wavelength of the light, then most of the light is reflected in the specular direction. And the formula governing the roughness of the surface and the wavelength of light and angle of incidence is like this. This is reflectance of the surface. This is the reflectance in case of ideal surface. And this is sigma is the RMS roughness of the surface. Theta is the angle of incidence of the laser beam or light on the surface. And lambda is the wavelength of the light. So based on this principle, using this formula, we have calculated the RMS roughness of the surface, which is sigma, by calculating the reflectance. So it is required to measure the incident intensity and the reflected intensity. So we have made laser to fall on the sample surface near grazing incidence, that is near 80 degree of angle of incidence. And we have taken a sample using a beam splitter of the incident light and made it proportional equal to the output of amplifier image equal to the intensity of light which is falling on the sample surface. Then at the specular reflectance angle, means when angle of incidence is equal to angle of reflection, at this angle we have kept another photodiode to measure the specular reflected intensity. Then these two intensities are converted to voltage and through amplifier and fed through a multiplexer to a microcontroller. They are digitized using ADC card, and the microcontroller then use this formula to calculate the RMS roughness of the surface. So like this part of the instrument in which it the laser beam and the detector are used to measure the specular reflectance, it is implemented in this unit, which is a sensor head. Here we have mounted the laser beam, and there is a beam splitter which split the beam to a photodiode 1. Then this is the surface. The specular reflected light is collected by photodiode 2, and they are fed to the amplifier circuit, which output of which are given to the microcontroller. Then this multiplexer output is given through an ADC and given to a microcontroller, which calculates the RMS roughness of the surface and displays it. So this is a monitor unit which we have developed based on microcontroller 870-552. It is a 10-bit ADC, which is a keyboard for selection and displays both IX and I0. I0 is the incident intensity which is calculated from the reference photodiode, and this is a light which is reflected the specular direction which is collected by PD2. This gives the specular reflected intensity. So based on these two readings, we have calculated and found out the roughness of surface in the range of 0.05 to 0.2 micron, because we have used a red laser beam, so which has a wavelength of 670 nanometer or 0.67 micron. So our roughness of the surface should be less than that. So we are restricted to 0.2 micron, and it is very useful for routine comparison of similar surfaces. And it consists of three parts. This is sensor head, which is kept on the sample whose roughness is to be calculated. Then this is the monitor unit which displays the roughness value. And this is the power supply required for operation of this thing. And it has been found in-house use within our department, and for roughness surface measurement of metallic mirrors. So in conclusion, I would like to say that the above described methods are but a few of large number of application of laser-based instruments. It is nowadays finding wide application because of compactness and low cost and non-contact, non-destructive nature. The development in diode laser technology has benefited the growth of laser-based instrumentation, as it becomes possible to make compact, portable, and low-cost instruments using diode laser. And looking at the growth in this field, it is appropriate to suggest, I would suggest that a subject on laser-based instrument should be introduced at undergraduate level. That is my just vision. And the references, I would like to say that some of the very useful books related to laser-based instrumentation are, one is by Mr. Philip C.D. Hobbs on building electro-optical system and making it work. He has explained very nuances of the problems which one faces in developing a optical instruments. Then there is modern electronic instrumentation measurement technique by Cooper, which most of the instrumentation people must be reading. Then there is one book, good book on industrial lasers and their application, in which some of the applications which I have discussed are well defined and explained. Then photo detector catalog by UDD sensor and optics. Thank you.
Thank you,
madam.
sir.
Yeah.
Thank you, sir. Participants, kindly drop your questions. So there is a question. Is it possible to measure the inner diameter of the hollow objects by Shadow-Paul's technique?
Yeah, actually,
To measure the inner diameter.
Inner diameter. No, inner diameter can be measured. Some slight modification in the circuit would be required, because then there will be more pulses which will be generated. Like here, if you keep a object which is a hollow pipe, then you have to keep the object facing this along this beam direction of beam travel. So instead of one shadow pulse, there will be two shadow pulses generated. So we have to measure the interval between these two shadow pulses, because at one wall and another wall it will be generated. So by measuring the interval between those two shadow pulses, and it has to be properly aligned so that the light does not strike the wall of the pipe, and that way we can measure the inner diameter of the surface. It has to be properly mounted, and some change in the circuit of the instrument will be required.
Thank you, sir. Participants, any questions? There's some compliments, sir. Very useful session by sir. Something they're writing, the question was asked. She said, I got it, sir. I mean, as I understood. Thank you, sir. So, thank you, sir. We are really grateful for your stimulating talk on laser-based instrumentations. Sir, your session was very informative, well explained, and all diagrams you are so nicely with your work, what you are doing in the laboratory. So, and very much interactive. Sir, I'm sure your session would have triggered the mindsets of all the participants for this today's workshop.
Few of these instruments will be demonstrating in the afternoon session.
Thank you, sir. So all the participants will come back.
Yeah.
Sir, to demonstrate 2:30 Asim sir's session. Third session will start from 2:30 onwards.
Yes. Thank you, Padma, Dr. Padma, and thank you,
Let
Ravan.
us together once again. 2:30. Thank you, Devaki ma'am. Thank you, Lalitha ma'am.
Yeah.
Thank you, Padam.
Yeah, thanks.
So we'll come back at 2:30.
Okay. So now we can.
Yeah. Yes, ma'am.
Stop it.
Okay, ma'am. Thank you, sir.
Stop here. So मैंने ऐसे करना पड़ेगा, तो ये नहीं जा रहा है. And show.
उसमें जाके